Hi, everyone, and welcome to today's MRS On Demand webinar on Materials and Engineering, Propelling Innovation, hosted by Judd Reedy of Georgia Institute of Technology. I'm Bob Rockler. I'm the Virtual Engagement Manager at the Materials Research Society, and we're pleased to be teaming with the MRS Bulletin to bring you these monthly events. In this case, we have two this month, so thank you for those of you who have joined us for both. Our last webinar was Beyond Conventional Lithography, Patterning via Self-Organization and Self-Folding. It was a very, very good and successful webinar, and it's now archived, available at mrs.org/webinars. And the username and password that you used to get into this webinar today will get you in to see the archive of that as well. So a little bit about the series. Every webinar in the series is typically based on that month's MRS Bulletin theme topic. For today's webinar, we're actually backtracking a little bit. We went back to December 2015 when we had a special issue. Scheduling made this one a little difficult to do in December, so that's why we moved it to March, so that more people would be able to view it. So right now you're looking at a list of some of the upcoming webinars in the series. The next webinar is scheduled for March 23rd, and that's right before those of us here at MRS headquarters pack up to head out to the 2016 MRS Spring Meeting in Phoenix. We hope to see many of you there. The March 23rd webinar is titled Metamorphic Epitaxial Materials, and that one's going to be hosted by Christopher Richardson of the University of Maryland. And before we dig in, we certainly want to thank the organizations that you're seeing on the screen right now. These organizations sponsored the special issue of the MRS Bulletin. I should note that sponsorships are available for all of our upcoming webinars, and these sponsorships help us keep these webinars free of charge, so we are certainly grateful to all of our sponsors. I promise we're going to get started in just a moment, but first just a couple of quick notes about the format of today's event and also the player that you're viewing it in right now. If we start over at the left side of the player, a lot of you have already discovered the chat room. Please feel free to use that at any point today to talk to your fellow attendees. And below that, we have the Questions tab. So following the replay of Dr. Humphreys and Dr. Pollack's talks, we're going to have a question and answer session and a panel discussion with the individuals that you see up on the screen right now. So we ask that you please use the Questions tab to submit questions for those panelists. That helps us to manage the incoming questions much better than if you post them in the chat room. So, and below that Questions tab, you see a tab marked Resources. In that tab, we've put a complimentary copy of the intro article to the December Bulletin. There's also a link there to the MRS On Demand library of recorded talks. And there's over 1,000 talks in there that were recorded at recent MRS meetings. The username and password that you use today is going to get you in to see those as well. At the lower left corner of the player, there's a Request Support button. If you have any technical issues today, please feel free to use that button. That's going to get you personalized help to resolve the issue that you're having. Moving over to the right side of the player, there's a tab that says Notes. You can click on that and take notes during today's presentation, and those notes are going to be emailed to you immediately following the webinar. And with that, it's my pleasure to introduce MRS Bulletin Editor, Dr. Gopal Rao.
Thank you, Bob. And welcome everyone to today's MRS webinar presented by MRS Bulletin. So I'm Gopal Rao, the editor of MRS Bulletin. And typically each month, the theme topic of the month's MRS Bulletin issue is the topic of the webinar. But today's webinar is a little bit different and special. It's actually based on the MRS Bulletin special issue that was published in December of 2015, titled Materials and Engineering Propelling Innovation. So just some brief background to the issue in case you've not seen it, and I hope many of you or most of you have already seen a copy of this. The goal of this special issue was to capture the unique relationship between and the intertwining of materials and engineering. So materials enable engineering. Engineering, in turn, depends on materials to transform design concepts into physical entities. So this relationship really continues to grow as the societal demand for new products and processes is evolving and growing. There are about 20 articles in this special issue of the Bulletin, and that these include many different materials categories and the many interactions between material science and technology development. So, in essence, the overarching goal, I guess, of the issue is to stimulate dialogue and interactions between materials researchers and the people who actually use these materials and make products out of these. The guest editors of this special issue are V.S. Arunachalam of the Center for the Study of Science, Technology and Policy in Bangalore, India, and he's also associated with Carnegie Mellon University. Y.T. Cheng of the University of Kentucky, who will actually participate in the Q&A later in the webinar today. Dipankar Banerjee of the Indian Institute of Science, and Jim Williams of Ohio State University. So I really thank them for all of their efforts in putting this issue together. As Bob mentioned, the presentations that you're going to see today were recorded at the 2015 MRS Fall Meeting in Boston exactly 3 months ago, actually, on December 2nd. And in that session, we had 3 talks followed by a panel discussion. Today, we will present 2 of those talks by Colin Humphreys of the University of Cambridge and Teresa Pollack of the University of California in Santa Barbara. This will be followed by a recreation of sorts of the very exciting panel discussion we had in Boston. And we are actually privileged to have 5 of the panel members from that session participate in the webinar today, including today's host and moderator. And they will answer any questions you might have. I do want to note that there is a similar session planned for the spring 2016 MRS meeting upcoming in Phoenix at the end of this month. So if you're attending the Phoenix meeting, please consider attending this session as well. So talking about the moderator, it's my distinct pleasure now to introduce W. Judd Reedy as the host and moderator for the webinar. Judd is the Deputy Director for Innovation Initiatives for the Georgia Tech Institute for Materials. He has a PhD in Material Science and Engineering from Georgia Tech. He's also an adjunct professor of Material Science and Engineering and a principal research engineer on the research faculty of the Georgia Tech Research Institute. Previously, he has worked for General Dynamics, which is like a large organization, a large company, as well as in small business with microcoatings technology. So his expertise and experience spans the spectrum of small companies to very large companies and university as well. So his research focuses on energy, aerospace, nanomaterial applications, and electronics reliability. Judd was a 2015 volume organizer for MRS Bulletin, and he's also a meeting chair for next year's MRS Spring Meeting in Phoenix. So he is very active with MRS. He has won a number of awards, and I'll just mention the TMS, Electronic Magnetic Photonic Materials Division, named him as a 2002 Young Leader, and in 2015 he also received the Brimacombe Medal from TMS. He's also the recipient of the Innovative Research Award from GTRI in 2013, among others. He also happens to be a helicopter and instrument-rated fixed-wing pilot, and I don't know where he finds the time to do all of this, but I'm just happy that he agreed to be the moderator today. So, Judd, thank you for hosting the webinar today, and I'll pass this over to you.
Thank you very much, Gopal. And yeah, I actually don't really have much time anymore to fly my helicopters and planes around there, but every now and then I'll get up there in the air. But it's quite an honor to host and moderate this webinar. Greatly appreciate MRS reaching out to me to do this. And like Gopal said, it was a great session that we had at the last MRS meeting, and I really hope folks are able to attend the follow-up session that we'll be having here in just a few more weeks at the spring meeting. And so it's just with great pleasure that I get to introduce our 2 talks by Colin Humphreys and Teresa Pollack. Sir Colin Humphreys is a professor of material science and director of research in the Department of Material Science and Metallurgy at the University of Cambridge. He's also a fellow of Selwyn College at Cambridge, as well as a fellow of the Royal Society and a fellow of the Royal Academy of Engineering. He founded a spin-off company called CAMGAN. GAN is gallium nitride in this particular case, to exploit the research that he was doing, producing materials for low-cost LEDs. That company was acquired by a much larger company called Plessey, and now they're manufacturing LEDs out of Plymouth in the United Kingdom. You likely have either seen these bulbs on the shelves, or you may even have them in your house. He has won numerous prizes, so many that I won't name, except for the one that's probably the most impressive of all, and that's how he gets his first name, the Sir part. He was knighted for his services to science back in 2010. So that's obviously quite an honor for a citizen of the United Kingdom. Our second talk, and Colin's talk will be significantly focused on that gallium nitride technology. The second speaker is Teresa Pollack. I've known Teresa for at least a decade and a half now, it seems. She started her career at GE Aircraft Engines, but currently she's the chair of the materials department at University of California, Santa Barbara. She earned her PhD prior to that at Massachusetts, at MIT. She's also had academic positions on the faculty at Carnegie Mellon University as well as the University of Michigan. She's a member of the National Academy of Engineering since 2005, as well as a TMS fellow in 2009. She also served as president of TMS, which is a materials research professional society, much like MRS is. Her current interests include mechanical and environmental performance of materials in extreme environments, unique high-temperature material processing paths, ultra-fast laser materials interactions, 3D materials characterization, and alloy design. And with that, you'll most likely did not tune into this webinar to hear us talk. You want to hear them talk. So we'll get those talks queued up for you and ready to go. And then following this, we'll have some Q&A with additional panelists that I'll introduce at that time. Please feel free to put your questions as they come to your mind in the little box to the left of the webinar. And with that, I'll turn it over to Bob or Gopal to get the talks going.
Today's session, the program is up there. So we'll basically have 3 speakers speak first, and that will be followed by a panel discussion discussing different aspects of the topics covered in the issue and beyond as well. But first, it's my great pleasure to introduce our MC and moderator today, Anke Wiedenkauf of the University of Stuttgart from Germany. So Professor Wiedenkauf has been a full professor and is the holder of the chair for materials chemistry at the University of Stuttgart since 2013. So she has her PhD in chemistry from ETH Zurich, Switzerland, and she's also received the Venia Legendi for solid-state chemistry and material science from the University of Augsburg in Germany. After being a senior lecturer at Augsburg and then professor at the University of Bern in Switzerland, she then moved on to a couple of different positions, I guess, including at EMPA, the Swiss Federal Laboratories for Material Science and Technology. So Anke has published over 200 articles, maybe more at this point, and is an editor and an editorial board member of several journals, including, I'm very pleased to say, she's on the editorial board of MRS Bulletin as well. She has also organized several conferences, workshops, meetings on materials chemistry, including MRS symposia. She's been vice president and treasurer of the European Thermoelectric Society and is a member of the EMRS, European MRS Executive Committee, I think. Of course, she's received a number of awards, including the inaugural Kavli Foundation Lecture Award. So as I mentioned, she's on the editorial board. She's also on the board of MRS itself. So she's a perfect person, I think, to moderate this session. So, Anke.
So the first speaker is Sir Colin Humphreys. He is from the University of Cambridge and is a professor of material science and director of research in the Department of Material Science and Metallurgy at the University of Cambridge. He's also a fellow of the Royal Society and a fellow of the Royal Academy of Engineering. He earned his PhD degree at the University of Cambridge with an honor, and then he was also lecturer in Oxford and Liverpool before he was coming to Cambridge. Beside this academic activity, he also founded and directs the Cambridge Center for Gallium Nitride, and he founded a spin-off company which is called CamGan to exploit the research of his group on low-cost LEDs. So after selling this company, he is founded the Cambridge Rolls-Royce Center for Advanced Materials for Aerospace. And this center is now developing materials which are used in Rolls-Royce engines. So he also received many prizes. I will not list all of them, but for me very interesting is that he was knighted in 2010 for services to science. So it is really a fairy tale here. We have a real knight, and I would like to ask you to come on stage, please.
Well, thank you very much, Anke, for that kind introduction. Next time I'll come riding in my horse and you can share the ride. Thank you. It's a great pleasure to be here and to talk about innovation. And I'll just mention on the very first special issue that Gopal mentioned on energy, I was a contributor to that, and that was a wonderful issue. And this innovation issue is a fantastic issue. I mean, look through the articles, they're just fantastic articles there. So do take your free copy and read it and digest it and learn from it. So I'm going to talk about this real case study. In 2014, I think most of us here will be aware that the Nobel Prize for Physics was awarded to the 3 Japanese scientists. And the citation said, for the invention of efficient blue light-emitting diodes, which has enabled bright and energy-saving white light sources. So I think everyone was delighted to see this Nobel Prize going essentially to material scientists. And as an aside, there's no Nobel Prize for material science. That's terrible, isn't it? But there isn't. So you have to come in as a physicist or a chemist. But anyway, this Nobel Prize went through 3 Japanese scientists, and they did fantastic basic science and also exploited their science. However, what they did, which was fantastic, they grew GaN LEDs on 2-inch sapphire or less than 2-inch sapphire wafers. And the problem is that's still quite an expensive technology. So if we're really going to achieve widespread use of LED lighting, really widespread throughout the world and throughout the USA, then the cost has to be reduced. And so I'm going to talk about cost reduction and how innovative science and engineering can lead to that. This is from a United States Department of Energy report on GaN LEDs. And the first statement says, if you use GaN-based LEDs, you can reduce the amount of electricity used for lighting by 50%. And of course, you need to have has widespread uses of GaN LEDs to do that. There's this interesting comment also in the report. No other use of electricity has such a large energy-saving potential as LED lighting. It's a surprising statement at first sight, because at first sight you think, oh, if we make air conditioning more efficient, we save lots of electricity. If we make my electric toaster more efficient. And the reality is, things like air conditioning, electric toasters, heaters, dishwashers, clothes washers, they're already very efficient. To increase their efficiency by another 10% is very difficult. Lighting, as we'll see, is very inefficient. So The low-hanging fruit, to use that terrible phrase, is lighting. That's what this was identified by. The potential of GaN lighting. Lighting globally, and also in many countries like America, uses about 20% of all electricity. And if we use LEDs, as the DOE report said, we're poised to reduce that figure by 50%. So that means lighting will then use just 10% of electricity, so we will save 10% of all electricity. And in the UK, that amounts to about $2 billion per year, or £2 billion per year. I'll give the savings in the USA in a later slide. £2 billion a year. Think of a pound as a dollar. That's a rough conversion rate. So these big figures are quite hard to realise. About 2 years ago, the UK commissioned someone called Dilnot to do a report, and the government asked him how much extra we would need to spend on old people to look after them really properly. So he did this report, and he said the additional funding should be about £1.5 billion per year. And this went to the government, and the Treasury threw up their hands and said, we can't afford that, and they sort of filed the report away, and it's disappeared probably forever. So if you had widespread use of LED lighting, you would save enough money to look after all the old people in England really properly. And obviously the same would apply very much to America. This is the wall plug efficiency of light sources. What we mean by wall plug efficiency is the real total efficiency. So you take a lamp, plug it into a socket, this is the efficiency. It takes into account not only the efficiency of the light itself, but also any driver electronics. So incandescent light bulb, just 5% efficient. You get 5% light out for the electricity you put in. Halogen light bulb, 7% efficient. OLED panel, 15%. A long fluorescent tube, 30%. Compact fluorescent lamp, 25%. White LEDs, 35%. And these are all products you can buy now, and that is their wall plug efficiency. And you see already white LEDs are the most efficient light source, and they're 7 times as efficient as an old-fashioned incandescent light bulb, for example. In the laboratory, we have white LEDs, which are 60% efficient, and they will be coming onto the market in the next few years. So when that happens, we'll have a light source which is 12 times as efficient as an incandescent light bulb, and over twice as efficient as a compact fluorescent lamp. So these are really efficient light sources. Global impact of LED lighting. If 40% of the world's lighting was LEDs, then we could close over 500 power stations. Why aren't we doing that now? And the main problem is cost, as I will repeat saying. And of course, if you have 80% of the world's lighting LEDs, then you could close 1,000 full-size power plants, full size being 1 gigawatt typically. These are some of the growth facilities we have at Cambridge. So we have a system which will grow on 6-inch wafers and a system which will grow on 8-inch wafers. So these are industrial scale growth facilities we have. This is the latest DOE report, May 2015, and it's a really good report. And what they did in this slide, they just went out into the shops and they bought different light sources and they measured the light output. So this is nothing to do with the running cost, this is the capital cost of the light sources. So they purchased LEDs, and the cost per kilolumen of light emitted is $10. They purchased OLEDs, and the cost was $800. They purchased, still although they're banned probably, old-fashioned incandescent light bulbs, and the cost is $0.6. For CFLs, it's $2. And you immediately see the cost reductions necessary. So although LEDs over their lifetime will save energy compared with OLEDs or incandescent or CFLs, not many people will go and pay $10 for LED replacement light bulbs. So we need to reduce the cost by typically a factor of 5 if we're really going to get the widespread adoption of LED lighting throughout the world. LEDs now are just 5% of lighting sales in the USA. I think it's increasing rapidly, but when they went out and they did the report, that was a 5% figure. And the reason, again, is the cost. They're just too high cost. And people will buy CFLs because they're much cheaper at the moment. So what's presented with widespread use? Say it again, it's cost. And if we're talking now about innovation, then it's obvious what the solution is, what we have to try to do. There's a major market for reducing low energy products, and as a nation, as a world, we have to reduce our energy consumption. And to get widespread adoption, we have to reduce the cost. So that's the innovative challenge. How do we reduce the cost of LEDs so that they really become used in a widespread way? So low power LEDs, as used in children's toys, very, very cheap. High power LEDs used for lighting are expensive. In the UK, it cost me a few months ago £15 to purchase a Philips 60-watt equivalent replacement LED. It's now down to £10. I think in America it's a bit cheaper than that, but still they're more expensive than compact fluorescent lamps. This is DOE predictions in that report for 2030. They say if LED costs do come down, so we can make that step, and efficiency is up, then they predict that 90% of the US market, 90% of US lighting in 2030 will be LEDs. And I think the same will happen in the world. So we really have a dominant light source in the world of LED lighting. But the costs have to come down to do that. Interestingly, the electricity savings, if this happens with LEDs, are twice that generated by wind. And they're 20 times that generated by solar. And the annual savings, and here's a figure in the report, the annual savings the US will make by having 90% adoption of LEDs is $40 billion per year. It's just huge savings, huge financial savings. And of course, there are no subsidies for LEDs, as there are with some other forms of power like wind power and solar. So don't look at all these figures. This is just saying the commercial markets for gallium nitride are very large. So if you look at the top figure, solid-state lighting market for GaN-based LEDs, over $100 billion. Slightly down on that slide, all market areas forecast to have double-digit market growth over the next 5 years. And you'll notice on that slide there's also gallium nitride power devices mentioned and RF devices. And again, those are low-energy devices. So for an equivalent power electronics device, if it's made from gallium nitride, it consumes about 50% less energy than if it's made from silicon. So again, for power, gallium nitride is not only low energy for lighting, it's also low energy for electronic devices. And at the moment, electronic devices are probably 5 years behind the lighting devices in the research and development phase. And right at the bottom, the key to delivering is reduced cost. So my group was trying to solve this cost problem. And the reason these devices are expensive is that the gallium nitride LEDs, they're grown on small diameter small diameter sapphire or silicon carbide wafers, typically 2-inch diameter. And that's how they used to be grown. To reduce costs, one thing we've been pursuing is to grow on 6-inch diameter silicon wafers. And you can instantly see that should reduce costs because silicon is cheaper than sapphire or silicon carbide. And also, if you grow on a 6-inch diameter wafer, the processing costs of that wafer are not very much more than growing on a 2-inch diameter wafer. And on a 6-inch diameter wafer, you get 9 times as many devices as you do on a 2-inch wafer. And because the edge effects are less, you actually get 10 times as many usable devices. So you can see where these cost reductions come in on growing on a large diameter wafer and also on growing on silicon. And if we can do that, we substantially reduce the cost of LEDs, and that will enable the widespread use. So the UK can save $2 billion a year, and £2 billion a year, and the USA can save $40 billion a year. And in the UK, we could close or not build 8 large power stations. And I'd like to acknowledge my postdoc, Dan Danjou, who pioneered the growth of these GaN LEDs on 6-inch silicon in my group. So just to initiate our growth on silicon, when we started this work, all commercial gallium nitride LEDs were grown on sapphire silicon carbide. Our vision was to innovate and to grow on silicon. It all started with a 3-month exploratory grant I had in 2003 from the EPSRC, that's the UK Government Funding Council, which was called Exploratory Proposal to Grow and Characterise Gallium Nitride on Silicon, and it was just over £50,000. So that's how everything started, and we grew on 2-inch diameter silicon wafers then. And I'd like to thank and acknowledge this funding council, the EPSRC, for continuous support for my gallium nitride research since then. And that's really important. And for innovation, if you're in universities, it's really important that your government agencies fund you continuously to develop this, because we know in the materials area, development of products can take typically 10 years from start. And you really need that support to get through to the actual prototype device stage. So a message, to give to your funding council is really important. So why do we want to grow on 6-inch silicon? I've said some of the reasons already. Another reason is it's compatible with silicon processing techniques using a silicon foundry. So silicon has now moved to 12-inch, so that means there's a number of silicon foundries around which are 8-inch or 6-inch, which are totally depreciated and there for free to use if you have one of these. And the thing about using a silicon foundry is it's automatic and it has high yield. And the processing on sapphire wafers tends to be largely hand processing by comparison. And if we can grow on 6-inch, then we can probably grow on 8-inch and then grow on 12-inch for even larger cost reductions. So this gives a cost breakdown of package LEDs done by Yole Development in 2013. And if you look at the right-hand side, what you'll see is it's quite a complex situation trying to minimize cost. The cost of the substrate itself is only 11% of the cost of the packaged LED. So if you save on substrates itself, you don't save so much. If we look on the left-hand side, the cost of growing on 2-inch sapphire, the cost per millimeter of 2-inch sapphire is much the same as the cost per millimeter of 6-inch silicon. So as I said before, you get 10 times as many devices on 6-inch silicon than on a 2-inch wafer. And so you immediately get quite a large cost saving from that. The alternative is to try and grow on 6-inch sapphire, which again gives this reduction in unit cost. But you see 6-inch sapphire is about 10 times more expensive than 6-inch silicon. So if you have 6-inch silicon, you improve the substrate cost and save about 10% of the total cost by doing that. But you get much greater savings, it turns out, because if you grow on silicon, you can then enable cost reductions in the processing, in the packaging, and also in the phosphors. Now, I don't have time to deal with that, but just to say, if you grow on 6-inch silicon, you can then do chip-scale packaging rather easily and chip-scale optics. And this hasn't yet been applied in the gallium nitride area, but it's starting to be applied, and these will bring significant savings. And the company which is exploiting that technology, Plessey, which I mentioned, they reckon that the total cost reduction of a packaged LED grown on large area silicon is typically 5 to 10 times. So these are just the sort of large cost savings you need if these devices are going to be really cheap and compete with compact fluorescent lamps. So problems with the GaN growth of 6-inch silicon. The first one is cracking, because you grow at 1,000 degrees centigrade. When you grow the gallium nitride on the silicon, the thermal expansion coefficient mismatch is 52%, which is huge. The gallium nitride is in tension when you cool down and it cracks. So you have to put in compressive stress when you grow deliberately to counter this tensile stress on cracking. The other factor is the dislocation density is very high when you grow on silicon, about 10 to the 10 per square centimeter, and we have to do dislocation reduction techniques. And those are both quite difficult, but they can be done. And we can now routinely grow gallium nitride LEDs on 6-inch silicon with no cracks at all and with relatively low dislocation density. And this is an example of the first fully processed LED on 6-inch silicon wafer in the world, which the growth was done by my group in Cambridge, and then it was processed by RFMD on a 6-inch processing line. And the left-hand side shows a 6-inch wafer, totally crack-free. There's a variety of different LED sizes on that, so it's a sort of test wafer. And then the top right-hand side shows a number of these LEDs of different sizes, and the bottom diagram shows a current being passed through the LED. It's actually emitting blue light that's so brilliant it's saturated the detector, so you just see it as white light. It's actually blue light being emitted. So how to exploit our research? Because it's all about innovation. So the first thing to say is it can be difficult and it can be tricky. And we started having a project with a company, UK company called Filtronic, and this project started in, I think, 2005, I think, or 2006. And they were going to manufacture LEDs in the UK, and after 18 months, they fell on hard times financially, and they had to sell half of their manufacturing facility to RFMD, an American company, and so they no longer were able to manufacture our LEDs. They sold off their processing lines. But RFMD took this project over and spent another 18 months on that, and as I said, they successfully processed that wafer I showed. But after 18 months, they fell on some hard times, and although our MD in the UK wanted to continue with the project, the management team in the USA said it wasn't their core business, so they stopped the continuation. So those exploitation routes were closed. I then gave a talk in the UK, and someone from a company called XFab was there, and they said, oh, we'd love to manufacture this product. So they took it along, and they worked on processing for 6 months. And then their parent company, XFab in Germany, decided to close the UK factory. So we tried the sort of conventional routes for exploitation, or a conventional route going through other big companies, and we kept hitting these brick walls. And so we decided to go it alone and set up our own companies. And so we formed a company with Dan Zhu, who was the postdoc who was exploiting this, who was developing this technology, Louis Yu, who was a third-year research student, and we decided to set up this company. And the first thing we had to do was get a name, because the name is quite important for a company. So we thought up CamGan for Cambridge Gallium Nitride, and we set that up in 2010. And I was the CEO of the company, and we then talked to lots of people because I had no experience of setting up a company. And a few people said to me, Colin, you may be an okay scientist, but you'll be hoped as a CEO, you've got no experience, you need to find a good CEO. And initially I thought, that can't be right, I can run a company, but after sleeping on it, I realized they were absolutely right. So we got a proper CEO and who did a great job, which I could not have done. So that's another message to give to people here, I think, that, okay, a few academics are really good at running companies, but most of them really are not. And you need to get people with experience of running companies who've got a good track record and then let them take over. And so they got this CEO. And it's an interesting story. So Andrew Lin is a materials scientist who was in the department at Cambridge, and he'd set up his own company and he developed it very successfully. So he got experience. And he'd helped us, unpaid, he'd given us advice. And so I asked him to be the CEO, and he said, Colin, he said, well, for most people I charge £150,000 a year, but for you, £100,000 a year. So just think of dollars instead of pounds, it's approximately right. And I said, I wouldn't, Andrew, we need to think about that a bit. And at the same time, we'd applied for a research grant from something called the Carbon Trust in England, and which funded research on low-carbon technologies. And I got phoned up by a person from the Carbon Trust, and he said, can we come and discuss the research grant with you to see if we can fund it or not? And he came along with another person from the Carbon Trust, and we sat down to discuss this grant proposal. And he said, Colin, he said, we're not actually here to discuss the grant proposal. He said, because I've been so impressed with this, I've come along to say I want to be CEO of this company. And he brought along someone to be the CFO. And I said, well, how much will you charge? And he said, £120,000 a year. And I said, well, it so happens that just 3 days ago, I had another person who's also very good who said he'd do this for £100,000 a year. And he said he would do it for £80,000 a year then. And so I wasn't trying to play them off because, I wouldn't do that, but it so happened this was a situation we're in. So I went back to Andrew Lim and said, well, we've had someone from the Carbon Trust who's very good, and he'll run the company for £80,000 a year. And Andrew Lim said, I'll do it for £50,000 if I get some shares in the company. And so I said, okay, let's think about that. And I went back to the Carbon Trust person, I said, just for information, and said, we've got £50,000 on the table. And he said, I'll do it for free if I have shares in the company. So I went back to Andrew Lin, and he also said he'd do it for free. And since Andrew, they were both very good people, so it's genuinely hard to choose between them. But because Andrew had been helping us already, I felt, more a moral obligation to him. So we went with Andrew Lin, and so he did it for nothing. And Andrew then said we need the chief finance officer, and he knew a very good person. And I said, fine, Andrew, but get him for nothing. So he got him for nothing. So I had no idea you could do this sort of effect. But if you set up a company, you can try, just offering shares in a future company rather than providing money for salaries now. I'm not sure if that works in America or not, but it worked in England. So we set up CamGan, and although we believed in the company, none of us really wanted to put our own money in, not at this stage. And of course we had a research student who had no money, a postdoc who didn't have much money, and I didn't have a lot of money. So we tried not to do that. And we realized the first thing to do was have a company address, and we decided at this stage we didn't need an office. We could have meetings in my house or meetings in a laboratory. And so we just needed an address. We needed a letterbox. And in Cambridge, there's something called St John's Innovation Centre, which provides a virtual office, and it's £40 a year. I mean, think of $40 a year. It's really cheap. So it's a great bargain. So that was our address, our company address. And it's a virtual address, but letters would be delivered there. And we go every so often and collect letters. I phone up, say, letters come. So that was the idea. And then we registered the company at this address, at Company's House in London. And it's very cheap. It's just £100 to register a company in England. And it's probably the same in America. I don't know, but you all know here. So I was amazed how cheap it is to set up a company in principle. If you get, a CFO for free and CEO for free and these other deals. And so then we had CamGam business cards printed, which we would give out to interested people. And then we had discussions again. And in Cambridge, there's a lot of people who help you for free. There's business angels, and they talk to you. And there's other people. And they're all very good. They'll help you for free to a certain extent. And after a time, they'll say, OK, you now have to pay us, or, we now want to get involved. But you get a lot of good free advice. So we were advised to filing a patent's really important, because that shows that you've got some innovative new technology. But we were advised to keep back some important know-how, because if you reveal everything in the patent, there are certain countries who will just use all that information and you have no comeback on them. So we filed a patent, and we did keep back some important know-how. So the patent was a framework of the know-how we had, and then we subsequently filed another patent. And then we set up a website, and that was very important. And again, we were advised we needed professional help, because the website is really important. You'll see why in a moment. And so Andrew Lin, our CEO, he said he knew a very good website designer who had had a family and was at home, and she was very keen to get back into business. But he said, I think if I approach her, we can get a good deal from her. And she was very keen to write us a website for virtually nothing, because she would then use this when she went out for a full-time job and saying, this is my recent work. And so she put up a really great website, and again, we paid virtually nothing for that. So we didn't spend a lot of money. And then we started to write a business plan, which was quite difficult, because to really exploit the technology, you need 6-inch or 8-inch processing lines, which of course we didn't have. And there aren't many in the UK, and those are owned by other people. So, we were wondering how to write this business plan when people who'd read our website started contacting us. So, and that really amazed us. So we had a significant interest from China, Japan, America, and this company in England called Plessey. And we had the CEOs from these companies came across to Cambridge and chatted with us, and they were all interested in acquiring the company. And and it was hard to make a decision, but I made the decision that since the UK had funded, all our research, we should go with the UK if we could. And so we went with the UK company Plessey for 3-month talks. So basically, you get to a stage, you talk to these other companies, then you tentatively choose a company, and then you enter into quite detailed negotiations for typically 3 months. And that's what we did. And then the other companies you didn't talk to. That was in 2011. We had these talks, and it all went really very rapidly. And Plessey acquired both the companies in February 2012. And Cambridge University said this was one of those most rapid acquisitions and exploitations they'd known. Plessey hired 3 postdocs from my group, and one of the things they did was to help to transfer the technology, so that's very important. So they took the patent and the know-how with them to transfer the technology. And people said transferring this technology might take 2 years, but it was transferred in 8 weeks. So that was a very, very rapid transfer. And Plessey sold 2 million LEDs. They're manufacturing now. They sold 2 million of these LEDs in 2014, plan to sell 50 million in 2015, plan to add 400 new jobs by 2017. And they're just selling the chips at the moment, and I'll give you some examples in a further slide. So this is, on the left-hand side is our reactor, which grows on a single 6-inch wafer. Right-hand side, a Plessey commercial scale reactor, which grows on these 7 6-inch wafers. And we transferred that technology across in just 8 weeks. I should say Plessey then had a lot more work to do. We transferred the active region of the gallium nitride LEDs. We didn't transfer any processing because we didn't do the processing ourselves. So Plessey had to develop that. They had no experience of LED growth. They had no experience of gallium nitride before, so they had a very steep learning curve, and they did remarkably well. So this shows some of Plessey products you can go and buy now. I'll just point out on the left-hand side, these are LEDs on metal filaments, which can be used in filament light bulbs, because if people want to have replacement light bulbs, a lot of the public like a light bulb which looks like the old incandescent light bulb, and this looks a bit like it. As you can see the filaments glowing on these light bulbs. Plus, you're also making micro LEDs, dot LEDs, which are used in wearables. And what you don't know if you're buying a product that's got the Plessey LEDs in, because they're selling these LEDs to a variety of other companies who are then putting them in their products. And the Plessey plan is to expand and to market the total light bulb themselves in the future, and then to expand into power electronic devices. So the Plessey success, so when they acquired us, they raised millions of pounds in those 2-year periods from private investors. These are wealthy families. Again, I had no idea there are these wealthy families around who invest in all sorts of projects. And the first wealthy family was 2 Turkish families, and they've been going for years. And these are the grandchildren who are now investing, and they invest millions of pounds in all sorts of things. They recently bought an airline, and so they invested. This is the most scientific thing they've done. And it's long-term, it's patient funding, it's wonderful. And they get involved, and they're really interested in the products. So 2 Turkish families. And then some more money came from Russian families, so that they're investing. And then just in September this year, Plessey raised another 60 million, and 30 million was from the Deutsche Bank in Germany. And so it's that additional funding which will enable Plessey to increase its production by 30 times, and they plan to treble employment to over 500 people by 2017. And then just last month, in 2015, Plessey was named Company of the Year by the National Microelectronics Institute. So Plessey are really doing very well. And it's such a pleasure for the people in my group and also myself to see our research exploited by industry in this way. And this is now the final slide, because this is all about innovation. So what I've learned to how to exploit research, and some of these things are obvious, but it's good to remind people perhaps. So what we did was to identify a major need in society. A major need is to reduce energy consumption and reduce the cost of LEDs. And of course, it may be a minor need you find, and that's fine, that's also good. The good thing about a major need is if the market is very large, you only need a small portion of that market to still have a substantial company. So we were lucky that we were working on LEDs. That turns out to be a major need in society. And then you need research funding, and that's really important because you need to take things through to a prototype device stage. Identify a solution, so the solution was GaN on silicon instead of GaN on sapphire. File a patent but keep some know-how, very important. If you're talking to other companies, they really want you to have patents. And if you keep some know-how behind, that puts you in a very strong position. We try to exploit through an existing company. We tried to exploit through several existing companies, and we failed for reasons that these companies hit financial problems. So we decided to set up a new company. In fact, we set up 2 new companies. And that was a lot of fun doing that, and we learned a lot. Obtain a good CEO, really important. So this is a message to academics here. Most of you should set up a company, you should obtain a good CEO, and he makes things happen. He or she makes things happen. Have a good website and business plan, really important. We were lucky. We didn't get to the stage of a business plan because our website was so good. It attracted people internationally who were interested in coming and talking to us. And then this is the final thing to say. This is Winston Churchill. You will hit, although it is great fun setting up a company, you will hit problems you don't expect. So you need to persevere. And Winston Churchill said, never give up, never, never give up, never, never, never give up. And so that's what we found we had to do. So thank you very much.
This is Teresa Pollack, and she's also from California, from Santa Barbara, University of California, and she is one of the members of the advisory group for this issue. And in the moment, she serves as a chair in the materials department at the University of California. She holds a PhD degree from the MIT, and she started her career at GE Aircraft Engines, where she worked then on advanced superalloys for gas turbine engines. In 1991, she joined the Materials Science and Engineering faculty at Carnegie Mellon University, where she was the Alcoa professor until 1999. And then she moved to the University of Michigan. After she was elected to the National Academy of Engineering in 2005 and as TMS Fellow in 2009. She was TMS President in 2005, and her current interests include the mechanical and environmental performance of materials in extreme environments. Okay, so Teresa, we're looking forward to your talk.
Thank you very much, Hanka, and good afternoon, everyone. It's a pleasure to be here today, and I hope that we caught some of the people as they walked by. So my assignment today, as I understood it from Gopal, was to cover some of the territory between discovery of new materials and their translation to engineering. And I think it's no accident that Gopal selected 3 speakers who had really long flights, because a FedEx package with this bulletin showed up on my doorstep right before I left for the airport. And I had the pleasure of reading the entire thing on the way here, and it's really very well done. So congratulations. All right, I'll get further away. Is that better? Okay, good. So yes, as you heard, I have had both industrial as well as academic positions. And so I was asked to sort of say a little bit from both perspectives. And so I'll attempt to do that without a great amount of detail about my research, but rather with an eye to what's going on with regard to these translational issues, both at MRS and in the broader materials community. Okay, so let's start with materials discovery. I think everyone is here today because they have a passion for this part of the problem. And we have a fantastic toolbox to work from. And some of us spend a lot of time where the orange circles are. And there are, in my mind, nearly limitless variations of macromolecules and copolymers and molecular architectures and so forth. And so that means to me that there's nearly limitless opportunities for discovery. If you sort of swing more toward the hard materials and wander through the central parts of the periodic table, it's remarkable how little we still know. If you take perhaps the 81 useful elements and ask yourself how many binary, ternary, quaternary diagrams there should be to describe the behaviors of these systems, it goes from 3,240 to 85,000 to nearly 5 million. And of course, you know, within each one of those systems, there are an almost infinite number of states that we go through as we process materials. And so it's safe to say there's, again, a lot that we don't know in these systems. And just to highlight that point, we actually have a pointer here. If you imagine a ternary diagram, for example, and a binary to start with, I guess. If you imagine a binary diagram and ask yourself, if you ask how many of those binary diagrams have unique compounds that sit in the center of the system, there's basically 2 additional compounds for every. If you go now to the, we're having a lot of problems here. Okay. Now, if you go to the 3 combinations, there's 13,000. So there's only like 1 per every 5. And if you go to 4th order systems, there's only a few known compounds that don't appear in any combination of the ternaries. And in fact, just a couple of weeks ago, somebody reported a new L12 intermetallic that didn't exist in any of the constituent ternaries, but suddenly appeared in quaternary space. So in all of these cases, there's still plenty of room for discovery. I think there's some discussion about this in the articles in the journal. And I would argue that there's plenty of space left there. Now, speaking of space, the article written by Jim Williams, I think, sort of shows this nicely. If you sort of look back in time at an Ashby map at how much of the space is actually occupied by available materials, you can see that the space is rapidly expanding. And Julia just showed us one of the ways of doing that a moment ago. And so the discovery part, I think, is alive and well. And again, that's why many of us are here. Now, the bigger problems come when we think about translating these materials that we know and love into engineering products. And this usually takes one of 2 paths. And I predicted that Colin would talk about that path, and he did. We can think about startups and taking the new materials to market in that mode. There are 2 excellent articles that talk about the challenges of doing this in the issue, and so I encourage you to look at those. The other mode would be to go with some of the more conventional, well-established companies who need these materials, but also have fairly strict systems for maturing materials from the time they're discovered until the time that they're actually used. And there are examples in the issue from both aerospace as well as automotive. And of course, we know well that we'd like all of those systems to be safe, and so there's a very good reason why it's difficult to get new materials into those systems. And so this, of course, always immediately ensues to a discussion of the Valley of Death. And this is a well-known problem. There are 3 papers in the issue that spend some time on this topic. And the Valley of Death really is this big chasm between the prototype and the actual application. And I show a figure here from the paper by Williams and Banerjee. And I like this figure because they actually spent a little bit of time mapping out what's in the Valley of Death. And so these concentric circles I've written here, some of the things that they view as most important about the Valley of Death. And I'll say a few more things about a couple of them. So if you look in this first column, there's a lot of words about supply security, geopolitics, the supply chain. And this really comes down to how scarce are the materials that we'd like to use. And I show here a couple of charts from my colleague Ram Sasadri at UCSB. And you may not be able to see it very well, but basically he's plotting scarcity and the HH index, which really sort of captures other aspects of scarcity in terms of production or politics of not being able to access certain materials in certain regions of the world. And so as you go from blue to red, we become more scarce and, of course, much riskier. Now, this shows up in all classes of materials. Thermoelectrics are sort of the current one where you see this a lot. We have a way of plotting figures of merit. We want to think about ZT. And so then we go and harvest the properties or predict the properties and look for high ZT. But if you plot scarcity on this axis against the HH index, of course, we'd like to be down here in the corner where we have things that are not scarce and that are going to be available. And what you'll see is that this is a good way of guiding the search, because some of the things up here that have very good properties of thermoelectrics simply aren't going to be available. And so that would be the first question the academic is asked when they go to someone to make their thermoelectric. Where would I get that material, and why would I want to make anything out of that? And so this sort of information is always something to keep your eye on. Now, as you heard earlier, I have had some experience with the business of being the material scientist in a place where people design big, complicated systems. And I show here my view of this. There's always the material scientist who says new materials equals a better world. This photo is from Sandia National Lab. This happens to be an ex-student of mine, so I know he loves materials. This gentleman is working on designing a reactor vessel for a nuclear power plant. And so for him, always, new materials equals much higher risk. And so in that context, for big, complicated systems, they're really viewed as a necessary evil. That is, no new materials unless I absolutely need them. And so in this context, and maybe we can talk about this more at the panel, the pull is much easier than the push. If you really need the material and there are no other alternatives, then it's much more likely to get a material from the lab into a system. So the real problem at the root of all of this is that the process that you need to go through to get the material from the lab into a system just needs to be faster. It's incredibly slow. And if you've never been through this process, you may not realize that some companies have very elaborate systems for taking a material from discovery to production. And these systems are typically laid out in technology readiness levels. They may be called something slightly different, but there are many companies who have large systems, large handbooks, very detailed documentation on what constitutes making the step, say, from TRL 4 to TRL 5. And so a lot of things have to happen, and they're very expensive. And because they're often very experimentally intensive, make the component intensive, then they're difficult to do, and that's why the Valley of the Deaf is here in the middle. And so if you look through the issue, you'll see that this business of being faster comes up a lot. And so there's 5 or 6 papers here. And so Colin spent some time talking about cost. That's a huge thing, and the other thing is speed. And so my focus here to a greater degree will be on speed. Now, speaking of speed, this goes back to a development. So this development project consisted of discovering a new single crystal material for aircraft engines. It's now known as Rhenean 6. And so this was actually my first job after I finished my PhD. And you don't need to look at the details here, but it's very revealing what went into the patent. And so if you look closely at this table, you'll see a bunch of elements, and you'll see systematic 2-level variations of the chemistry. And this was absolutely the way that everyone insisted that you discover a new material. So you design a large experimental matrix, you spend years making small pieces of the material, and then somewhere in here you discover the optimum. Now, I'm a very impatient person. This is a slow process. You can see that by the time the patent's even filed, I'm already gone. I'm in Pittsburgh. And so, and you can bet that it was many, many years later before this material actually flew in an engine. And so the real question is, how can we do all of these things faster? Now, when I say all of these things, I mean not only considerations of these supply issues, but also other things like how do we design things faster, how do we predict what the properties are, how do we predict what the debits might be when we make more than just a handful of the material. Now this is not really a new problem. There have been many, many reports over the years at the national academies, for example, that have focused on the speed issue, the valley of death. And so I ask now what's different. And I think the thing that is different and is changing the landscape very quickly is a couple of initiatives that are going on in the US and similar initiatives going on elsewhere in the world that have to do with the business of integrating computation with experimental tools and big data in much more intelligent ways than we've ever been able to do before. And so I show here a couple of reports. One in the US, which was very helpful to pushing all this forward, is a study on integrated computational materials engineering. Sharon Glotzer did a study on simulation-based science and engineering. Ultimately, a lot of people investing time in thinking about what is possible and how we can do this faster led to the Materials Genome Initiative, which is very poorly named, but that's what we have. The White House picked the name. So, but this initiative really aims at developing new materials twice as fast at half the cost. And so again, these are the two big issues, speed and cost. And the focus of this initiative is really the business of integrating computational tools, experimental tools, and digital data. This has been going on for a few years now, and I think there's been a lot of interesting and very hopeful things from the point of view of getting materials from the lab into applications. And I'm not going to discuss this in detail, but I just show a few highlights here. First of all, there's the increasing computational power that we have. It's getting better and better every year, including GPUs. And so that actually enables us to look at materials that are much more complicated than we were ever able to do so before, and to do it in reasonable lifetimes, meaning graduate student lifetimes, because that's where a lot of the basic research is going on. There are projects like the Materials Project of Gerd Cedar and Kristen Pearson at Berkeley that are building databases of material properties by automating DFT calculations and putting the results into databases. And it's remarkable how fast the information is accumulating. So one can now go and use this information without having to redo the calculations. So a tremendous resource. There are books on computation, educational programs, summer schools, workshops that are emerging because this way of doing things in a more computational intensive way, of course, requires a lot of different skills. There are agencies who are now specifically asking, at least in the US, for proposals which combine experiments, theory, computation, and really work at making those things work together and work together quickly. There are new software developments in terms of dealing with all the data. I show here the Blue Quartz software, which is really aimed at dealing with large 3D data sets. There are some informatics companies that are emerging, and so on all of these fronts, experiments, computation, and data, we have a fairly rapidly changing landscape, which I think is hopeful from this point of view. And then I'll just finish by saying whenever people talk about the MGI or some of these other similar initiatives, there's always this reaction is that we can't do everything computationally, and that's absolutely true. What we have to do is use experimental tools and computational tools together intelligently. And so rightfully so, I think, there's an entire article about characterization in the issue, and MRS has certainly not forgotten the importance of that. And so what we need is characterization at all length scales, of course. We need things like combinatorial synthesis. We need to bring forward ways of rapidly designing and making materials. So there's a couple of articles about 3D printing. And so in all of these cases, again, we're starting to deal with big data problems. So the amount of data you can get from the synchrotron in a week usually takes a year to process. And so there are some real opportunities in instrumentation in terms of automating the data and automating the way we deal with it, because doing it manually going forward is just not going to be possible. And I'll just give you one short example of our own situation with regard to the 3D data. Now, I'm going to show you what motivated this set of experiments that I'll show in a second, but it's really the business of property prediction. So if you imagine whatever property you're interested in the context of the materials you're looking at, it could be a property which is sort of very sensitive to the nanostructure of the material, or it might be a property like fatigue that's very sensitive to the extremes of the features in the material. And so how well you need to know the material at any given length scale is, of course, dependent on what properties are important. And so we're getting pretty good at getting properties down here. And part of the reason why we're getting pretty good at that is that we don't really need to understand huge volumes of the material in great detail. However, if we're going to ever get around to sort of predicting some of these things up here, we're going to need a lot more information. So I show you here just one example of a new instrument which we've developed to sort of address that point. And we call this system the tri-beam system. And basically what we've done is taken a focused ion beam platform and integrated a femtosecond laser with this system. And so we call it the tri-beam because we now have an ultra-short pulse laser beam, 150 femtosecond pulses, the electron beam, the ion beam, and multimodal detection. So we can get crystallography, we can get chemistry, we can get structure and morphological distribution. And back to the speed issue, we can do this fast. So you've all seen focused ion beam 3D data sets. They have usually taken about 6 months to gather. This is 1,000,000 times faster because the femtosecond laser can remove material layer by layer without any significant collateral damage. So I'll just show you one example of a material to make the point that it's fairly materials blind approach. We can put a polymer under the beam. We can put here, in this case, a mixture of tungsten and copper, so two very different materials, and remove material layer by layer and get the kind of high fidelity information that's needed to develop property models. So I show here a movie of the material coming off the surface of the copper tungsten composite. You can see a few voids here. And basically, the material removal is now free. It takes a few seconds to remove the material. It, of course, takes much more time if you want to get chemical information or crystallographic information. And so you can fully automate this and get those sorts of data sets now in a couple of days. And so here, for example, is that data set, 30 hours worth of it. And then we, again, have a data problem because in every slice, there's about 1 gigabyte of information, and these data sets, depending on how much information you gather, can quickly become terabytes in size. That does bring up the question, how much information is enough? And that goes back to, well, what property do we want to predict? And so in this case, this material, you sometimes intentionally use it and ablate the copper out for cooling purposes in hypersonic vehicles and things like that. Details don't matter. But what I show here is the big data set with subsamples. And what I'm doing is changing the sample size and then calculating, in this case, the permeability, because that will be important to the ablation of the copper. Now, for engineering properties, we don't just need kind of a mean prediction. We need statistics, right? Real engineering systems designed based on minimum properties. And so what we're trying to do here is build a methodology for doing that. And so what I show here on the property end, the modulus and the permeability, and I'm showing these properties as a function of the sample size that was subsampled. And so now we can start assigning properties with some degree of confidence. So I know the modulus of this material will converge at 95% confidence if I sample a box that's 60 cubic microns, for example. And so it gives new ways of trying to be more quantitative about what we're doing with the materials. And so you can do this for properties. You can also do it for aspects of microstructure. And so in these sorts of systems, you have to converge everything, right? You have to converge the microstructural features as well as the property features. Okay, so with that, I'll wrap up by saying, from the point of view of discovery, I think there's still much to be discovered. There's a little bit of speculation here about how fast we'll hit the wall and run out of discoveries. I don't think that wall is anywhere near. I would finish by saying that the theoretical, computational data tools, experimental tools, these things are all speeding up dramatically. And that's precisely what we need in terms of getting materials from the lab into applications. And so I will finish by encouraging everyone to read the very last article in the issue, which is entitled Materials for the 21st Century, What Will We Dream Up Next? So thank you very much.
Well, those were certainly some very interesting talks. I hope you enjoyed them. We now have a panel of several researchers that also participated in the event. With us today are Professor Y.T. Cheng. He's with the University of Kentucky. He did his undergraduate as well as graduate work from Caltech, and then has served beyond University of Kentucky also at the General Motors R&D Center. He's very, very active in the MRS Bulletin, also as MRS Fall Meeting Chair, the Journal Materials Research Editor, and even goes back to his graduate student days when he won the MRS Graduate Student. So it goes to show how long a relationship that you can build and how fruitful it can be. He's a fellow of APS as well as MRS. Has won several great awards. The ones I like the names of the best are Materials Engineering Outstanding Teacher Award and the Teacher Who Made a Difference Award from the University of Kentucky. He does research in the area of biomedical devices, conservation, energy, nanomaterials, and sustainable manufacturing. Our second panelist is Monica Backhaus. She is with Corning, did her studies with the University of Hanover in Germany, and has held a number of positions ranging from the research director at the National Research Center, CNRS, in Paris. Also has been on the faculty at Cornell University and a research scientist with the Max Planck Institute in Germany, as well as doing research at the University of Hanover. Her expertise is in solid-state reactivity and has been successfully applied to porous ceramics for diesel particulate filter applications, electrochemical NOx sensors, and thermoelectrics. Third is Greg Galvin. He is CEO of Rheonics Incorporated, as well as interim CEO of Mesmerize. He's got a BS from Caltech, as well as graduate degrees, including MBA from Cornell. He was also president and CEO of another company called Kionics. Is an inventor on 58 patents and was named Entrepreneur of the Year by Cornell University in 2014. He has launched these several different companies, sold them, something of a serial entrepreneur, so is obviously very well versed in what it takes to bring materials, technologies out of the lab and into real-life production and getting them on the consumer shelves. And then our last but not least is Suresh Babu, professor in Department of Mechanical, Aerospace, and Biomedical Engineering at the University of Tennessee. Also also holds the Governor's Chair for Advanced Manufacturing at Oak Ridge National Labs Manufacturing Demonstration Facility. If you ever get a chance to get up there to that facility, I've been there a couple times, and it is fabulous. A lot of excellent capabilities, in particular the 3D printing and additive manufacturing, and that's a key component of what his interests are related to advanced manufacturing, bringing it, again, out of the lab and into broader production and use. Some of his interests are on non-equilibrium phase transformations in materials subject to thermochemical, mechanical, magnetic fields, as well as the intersections between product design, manufacturing, and material science. Has done ample work with the American Welding Society, as well as ASM International and ASME, holds numerous awards, many of them from the American Welding Society, including the William Ergang Memorial Award, the Warren Savage Memorial Award, the William Sparagen Award, and the McKay Helm Award, all of which are for excellence related to welding. Now, we didn't have too many questions get submitted during the talk, so I've certainly got a few primed that hopefully our speakers can do. The first one is, what do small businesses need most to more effectively take advantage of materials developments? And I turn that over to whoever wishes to speak on our panel.
Okay. So this is Suresh. Let me go at it first. So as a part of this manufacturing demonstration facility, we constantly interact with small businesses too. The question is, what do small business need? I believe I'm looking at it from the technology pull point of it. Most often, the small businesses have some kind of a material or manufacturing processes. So it is the most important thing to find out an immediate application where that innovation can be put to test or applied. So I would say that'll be the first from my perspective. Even though I'm from a technology side, I'll always say that find an immediate application right away. I'll stop.
Greg, you've certainly formed several small companies. How can you speak to this from either side of that equation, from both the small business as well as the researcher side?
Sure. A couple of comments on it. I think from the business side, one of the challenges I've seen is actually finding material scientists to help the business understand how to use materials or manipulate materials. I mean, I'm very much involved right now with a additive manufacturing metals company, and finding metallurgists is really hard these days, since that field hasn't been all that popular in the last 2 decades. From the business side of materials, a little bit along Suresh's comment, one of the kind of economic challenge is typically that of being able to scale a materials development into a corporate activity. I was meeting last week with a Cornell PhD who had a polymer technology for fuel cells, and he had his little 2-inch diameter disc of this neat polymer that had very attractive properties. But, to turn that into something that's produced by the millions of yards, commercially relevant, is a huge challenge for a small company.
Monica,
I may add to those. I fully support those first comments. I would maybe add a little bit more. Since it's a small business looking for something, they do not have to waste a lot of money. They have to really be streamlined. So I suggest they should really make an excellent market and cost analysis before focusing and starting to do something in that area. And then the next step, look as well basically at the process, analyze the process, and see if it's scalable and can be scaled to production easily. And then they can use basically the outcome of these analysis and pick the best material, which may not look in the first time as the best material, but basically provides afterwards the best trade-off.
Thank you. Very good. YT, any additional comments?
I would like to add that perhaps we should improve communication between small companies and universities. And I worked in a big company in the past. Now I'm in a university. I found it's very challenging just to find out the needs of small companies that may have. And somehow, if we can improve the communication, that will be very helpful.
Excellent. We've got a couple of submissions from the audience. Considering long development times and huge costs associated with the development of new materials from lab to deployment, what are the potential ways that spin-offs or startups can be successful? VCs mostly focus on IT companies and look for quick returns. Federal investment, SBIRs, for instance, are not enough to support this cycle.
Hey, if I can take a crack at it. So I will give you a tangible example. There is a company called Local Motors, which actually believes in co-innovation. That means it works with the customers and then also distributed resources like technology development, and then they bring them together to develop a product. So they actually are trying to deploy automotives for custom design. So I think I would say that finding like people who want to work together in a co-innovation mode would be the right approach. I understand completely. Otherwise, it's too difficult to get the huge amount of investments right up front. So that's my 2 cents.
This is Greg. I would absolutely echo that comment. I mean, the fundamental problem with a material development from a commercialization standpoint is the material in and of itself is typically not the end product that's going to be sold in the marketplace. It's going to be used by somebody else to turn into an end product. And so the sooner that you can find that end use case and demonstrate it, the better off the company will be.
Good point. Yeah, I find with at least the research that I do, a lot of the materials work, it's at the component level or even subcomponent level, whereas what you typically sell are more systems related or something along those lines. Suresh, you made a great point about Local Motors. They were actually down here at Georgia Tech just a few days ago, as a matter of fact, and we met with them as well. It's a very interesting and unique business model. I look forward to potentially working with them in the future.
Yeah, they actually started a small local microfactory very close to MDF, and anytime any students can go and walk in and do it. There is no IT, nothing. It's just an amazing way my students are working on it. So.
Yeah. Monica or YT, any comments on how to get these things, get successful spin-offs and startups going?
Yeah, I agree with everything you said. I would add maybe that you really should try to narrow down the material, because often you look at a material family, and very often it's a big family, enormous family. And if you know what the target is, you can try to focus down, even if you're not 100% on top of what you need afterwards. If you have something which is close to the application and you get it there, then afterwards you get the money and support to do the rest of the development.
And I would like to add, in our educational institutes, like in the universities, we probably should emphasize to graduate students, during graduate student training, give them some entrepreneurship experiences and tools so that they can go out to the real world and develop companies based on the materials research they've done in their graduate school.
Yeah, I couldn't agree more with that, YT. There's certainly lots of schools are definitely beginning to ramp up their entrepreneurship and the understanding of the the business side as well as the scientific side among student classes offered. And I predict that that'll be a much more likely path that all schools will be picking up in the future. Speaking of the future, I mean,
this is Greg. Let me turn this around a little bit, and we'll have the panelists start asking questions. But I have a lot of experience with entrepreneurship at Cornell, and I wonder how it compares to the other institutions on the call, in that the entrepreneurship activities have largely not involved PhD students. They're primarily geared to the undergraduate population. Yet I think, particularly if we look at a materials type technologies, it's probably more graduate students that are going to be the potential entrepreneurs. And Cornell is just now kind of starting to focus some activities on helping to promote entrepreneurship among graduate students. How is it at Georgia Tech or University of Tennessee?
Well, Georgia Tech has a couple of things. We've got what we call the Inventure Prize, which is we've got sort of the senior capstone design effort that has its own prize and business competition type efforts, and then winners from that go on to compete against others, and that actually is I believe the Inventure Prize is it's televised and everything. I think it's this weekend actually. And then on the graduate, that's principally undergraduates, though graduates do participate in it, I believe, as well as high school students. On the graduate side, we've got an interesting program. It's called TIGER, and I can't remember what the acronym TIGER stands for. I think it's Technology Innovation Generating Economic Results, I think, something along those lines. But what it does is it teams students, PhD students from Georgia Tech with our university that's also here in Atlanta called Emory University that has a very strong business as well as legal foundation. So you get an MBA student, a law student, a PhD student coming together, meeting as coursework for both. It's credit hours for both schools, meeting and developing a business plan for that. And I've had one of my students participated in that, I guess 2, maybe 3 years ago now, and he found it to be very, very interesting. I'd be interested to know what's happening at Tennessee and Kentucky as well.
Okay, let me talk about Tennessee. To a certain extent, there are certain experiments we are trying. One is in the graduate studies. What we are doing is that instead of getting PhD assistantship, they are actually employed by companies full-time as an engineer, similar to the German model. And then they do research for their PhD while employed as an engineer. So at the end of the day, they may choose to stay with that company or get out and start the company. That is the one experiment we are doing. On the undergraduate study one, with this again being close to the manufacturing demonstration facility, many of them are exposed to small businesses who want to come and evaluate, and then they get paired up and then go do that. And then among in 2.5 years I've been at UT, there's one grad student who has actually started a company for additive manufacturing. Other than that, there are other activities there similar to senior capstone and everything. I just wanted to show some of the successful examples. I'll stop.
Yeah.
Well, that's some great examples of some successful. One of the questions that came in was, could we name any successful ones? And if we start rattling off names, we'll be here forever. I know Georgia Tech has what's called the ATDC, Advanced Technology Development Center, which is a incubator of sorts to help spur innovation and entrepreneurship and get these ideas matured into companies. And it's generated over 100 companies. So I encourage you to look up ATDC just on Google or your favorite search engine, and that'll have numerous lists. I'm sure Kentucky and Tennessee has quite a few, as well as pretty much any other school that you look at.
Right.
Okay.
Yeah, I agree with the earlier observations. There are more formal programs among undergraduates. For graduate students, we have some good experience of having graduate students co-supervised by people from industry, and they are exposed to industrial needs while doing the PhD research. We also use the local MRS UK chapter. The students would often organize seminars, not just technical seminars, but people come from industry to talk about career opportunities. So that is a positive thing. But I agree, we definitely need to do more among the graduate students.
I think also the NSF, IUCRC, and ICARPS are one of the things which people can access to get some more information to.
Yeah, YT, you brought up a great point regarding the role that professional associations can play in this, whether they're MRS or TMS or IEEE or American Welding Society or whatever. Would love to hear the panelists' ideas on how professional societies, what role do they play?
Oh, the professional societies play a critical role because many of the grad students and even undergraduate students, in my case, they go to American Welding Society. In addition to the technical meetings, they walk around where the real products are being sold. They understand how things happen. In addition to that, those people who are selling the equipment, they actually come to the technical talks and then they understand what is happening. So having that face-to-face meeting is much more influential than even reading a paper.
Anybody else? Certainly, from my perspective, I would agree that the face-to-face interactions, the networking, the chats around the coffee, and the various refreshments have always proved to be. You never know where accidental collaboration will come into play, and the professional societies, particularly the meetings, I think, are really a great way to rub elbows and get to know each other as people. And who knows, maybe, if you're going into business with somebody, they definitely need to have good technical skills, but also good, people skills and social skills and these sorts of things.
Completely agreed. Okay.
Let's see, we got one more here. That is, again, looking sort of towards the future. What hasn't popped up yet. There it is. What sort of materials, technological applications do you see changing the world in the next 50 years? I mean, that's hard to predict. Who would have seen the iPhone, for instance, when we were kids? But if there's some budding entrepreneurs out there listening and watching us, what are some areas that they might consider studying besides the obvious of saying to pursue their interests?
Wow, predicting future is really, really hard. Trajectories, the trajectories are dependent on the slope at which we stand, and the curves are complex. I think I would, if you are an entrepreneur, if you're thinking about being an entrepreneur, you just have to try. You have to, multiple times, you have to fail and you have to learn. And then by doing that, one day you will hit that magic one. So we talk about Apple many times. If you look back at Steve Jobs' own history, you can see how many times he fell down before he got up and came to that point.
That's a great point. And the failing, a lot of folks and even cultures entirely are very failure averse. But there's so many examples of having to fail, and that makes you succeed. But the key, I think, is always to fail fast.
That's correct.
Two comments on kind of materials future, if you will. One, which I think will probably reside more on the academic side than the commercial side, is, and as was in the last presentation in this webinar, was this ability to design materials computationally and predict properties. I think that will ultimately be looked at as something that significantly changed the world of material science. Then on kind of the more commercial side, I see this whole area of additive metals moving in a manner that would be very analogous to what happened with molecular beam epitaxy. So at the micro scale being able to create novel material structures that don't exist in nature. I think additive manufacturing in another few generations will allow us to create macro scale metal devices and objects that couldn't create in any other fashion by combining layers of materials that could not be combined in any kind of bulk process. And I think that on the commercial side will be one of the most interesting materials developments.
I completely agree. The ability to put different materials together, as Professor Ashby talked about in hybrid materials, will be helpful. And then, of course, there is a new trend of what can we learn from biology and biomimetic areas, and how can we get there also. So those are the areas worth considering.
Maybe I'll just add that this special volume of the MRS Bulletin, Materials and Engineering Propelling Innovation, that provides a lot of hints of what the future might be.
Yeah, including there is some area about how to package information within the materials itself too. So, for example, if material is working on it, so can we go back with the finding out where that was produced, what is the pedigree too.
Well, this has been a very enjoyable and interesting conversation with the panel as well as the talks. I appreciate all the panelists contributing their time, particularly YT. I hope you don't miss your flight there at Orlando's airport. And I definitely encourage everybody to stick around. There's a bonus session. We're going to have an additional talk that came from that MRS meeting 3 months ago. This one will be by Professor Julia Greer from Caltech, as well as the entire panel discussion that followed those talks as well. So you'll see and hear some of the same voices again, but not the exact same questions and discussions. Again, I thank all the participants, and Bob, I guess I turn it back over to you.
Yep. Thank you, Judd. So thank you, Dr. Reedy, and thank you once again to our speakers, Sir Colin Humphreys and Teresa Pollack, as well as our panelists, YT Cheng, Monica Backhouse, Greg Galvin, and S. Suresh Babu. And we certainly thank you all for volunteering your time to do this today. It's greatly appreciated. So we're going to begin our bonus material shortly. We have a talk by Dr. Julia Greer of Caltech and an extended panel discussion from our live event at the 2015 MRS Fall Meeting. So we do want to take a couple seconds to remind you about our upcoming webinars, particularly the March 23rd webinar. This one is on metamorphic epitaxial materials, which will be hosted by Christopher Richardson of the University of Maryland. And you can register for any or all of the upcoming webinars at mrs.org/webinars. And we certainly want to thank our sponsors of this MRS Bulletin special issue once again. You can find links to each of these sponsors in the Resources tab over on the left side of the player. And it's greatly appreciated that they help us out with events such as this. And we also invite you to take a short survey about the MRS On Demand webinar series. You can find that at mrs.org/webinar survey. Your feedback is certainly welcome and appreciated. And with that, we thank you for attending today, and we hope that you will stick around and to enjoy the bonus talk from Julia Greer, as well as the extended panel discussion. Now, we're not going to be doing any Q&A during or following those talks, but several of us are going to be monitoring the chat, so please feel free to continue the conversation there. So thanks once again to all of our participants today and to those of you who attended. We greatly appreciate your being with us.
Okay, so the second speaker is Julia Greer. She is from the California Institute of Technology, and she received her PhD in materials science and engineering from Stanford University. She worked as an integration engineer at Intel Corporations from 2000 to 2003 and was a postdoc fellow at the Palo Alto Research Center from 2005 to 2007 before joining the Caltech. A key focus of her research is the three-dimensional nano-architecture and designing experiments to assess their properties. Great. So her work was recognized among the top 10 breakthrough technologies by MIT's Technology Review in 2015. And she was selected as a young global leader by the World Economic Forum in 2014. She received several prizes, among them the Kavli Early Career Award in Nanoscience in 2014, and Young Investigator Lectureship in 2013 from Nano Letters. Then other early career awards from DOE and TMS and DARPA.
Thank you very much for the introduction. Thank you for inviting me to be here. I like to generally keep these talks interactive, so please ask questions as I go, but I'm not sure if this is the right format. So I'll just go through and please generate questions. So here's the title of my talk, Materials by Design. So this is kind of the threading theme here of this entire panel. Three-dimensional, okay, I think we all understand what that means. Nano-architected, this may be a little bit less clear. And then metamaterials, and maybe some of you are really familiar with what metamaterials are, and maybe some of you are wondering what the heck are metamaterials. So I'm hoping to explain all that in the course of my talk. So I'll begin by showing you this video, and I'm hoping that at least some of you can relate to something like this. So you go to the store, you buy all these things that you absolutely need, and the little plastic bags that you get for all the things that you absolutely need are just not strong enough to hold all the contents in it. So they're very, very lightweight and thin, right? So we know many other examples of these types of situations where you have a very thin material, which is very prone to breakage. For example, a wine glass, and then the balloons, of course, and then they're really meant to have 4 children. So these are all examples of the lightweight materials, and because of that, they also appear to be very prone to damage and tear. So this is a particular issue in devices, for example, or for butterfly wings or things hard biomaterials where their ability to be intact directly affects their functionality. So let's look at the different end of the spectrum. Let's look at the materials we know to be very strong. So of course, many of us probably traveled here by an airplane. You know they're all very, very heavy. So it turns out that the tremendous expenditure in the airline industry comes from the incredible amount of fuel that's required to propel a 1 million-pound machine through the air. So if you look at this is a Boeing 747, it weighs about 1 million pounds. So at about $3 per gallon, at 5 gallons a mile, my ticket to Boston should have cost me $45,000. So this is a very expensive industry. And so it turns out that it's the weight that really, the reduction in weight that would really help us. So these are all examples of materials that are very strong, but because of that, they're heavy and expensive. Now, let's look at more specialized materials, solar cells. So this is something that's a very common sight in California. Now, what would happen if this guy accidentally stepped off the roof? This would be bad news for everyone in that picture, because most solar panels are made out of brittle silicon. So if it falls down, of course, it would shatter. So yet again, specialized materials have this problem of being concomitantly heavy. And speaking of materials that need to be not heavy, whatever happened to that space elevator? Remember how we all were talking about the space elevator a while ago? Well, as far as I know, there still isn't one. And so it turns out that the reason why all of these problems exist is because of this very strong coupling between the mechanical attributes of materials and their density. So what I'm plotting here is all the materials that we know how to make today, and it's a log-log plot. So this is strength. I chose to plot the strength, but it could be stiffness, it can also be toughness, it can be almost any other mechanical attribute that's a figure of merit for its structural resilience as a function of density. And what you see readily is that the materials that we know how to make today are either simultaneously strong and heavy or lightweight and weak. What we don't know how to do is how to make materials that are both lightweight and strong at the same time. And this is why I'm showing this target region. This is a logarithmic plot, which means that even a modest increment within this space already represents a substantial change. So if there was some way to start making materials even here or something like that, that would already show us that it was already tremendously helped. So how do we do that? So I just told you that everything that we know how to make today is already plotted here. So how can we do this? So some innovation needs to happen for that. And the way we address this challenge is by applying the concept of architecture to material design. So here's the analogy. Let's look at the largest man-made structure. So this is the Great Pyramid of Giza. It stands at about 150 meters tall, and it weighs nearly 6 million tons. This is a tremendously heavy structure, and of course you can see that the amount of pressure it poses on its foundation is also quite tremendous. In contrast to the Eiffel Tower, which stands twice as tall, and it weighs 1,000 times less, without any sacrifice in the mechanical structural integrity. So what that tells you is that by clever engineering, you don't have to use quite so much material, and certainly a lot fewer slaves, to construct a structure that has all the mechanical attributes that you already need. So it's not necessary to use so much material if you are clever about architecting your structure. So that's the approach that we're taking. So we began this work a few years ago with these microlattices. So this is a microlattice that's made out entirely of nickel, and this is to scale. It's sitting on top of a regular dandelion in Malibu. This is not the world's strongest dandelion. There's nothing photoshopped about this picture. It's a regular dandelion, and you can see that this metallic foam that's sitting on top of this dandelion is hardly perturbing it at all. It's very, very lightweight. If I were to release it from any height, it would float through the air very, very slowly, slower than a feather. So these materials are very, very lightweight. But what we're after is not just the lightweight. We want the lightweight and some kind of a mechanical structural robustness. And so for that, we have to go down 3 more orders of magnitude, down to the nanoscale. So what we make in our group is nanolattices. And you can see that unlike the microlattice where your eye is able to resolve every structural detail, so you understand it's a structure, a microtruss that's made out of a particular metal, these are nanolattices. So when they sit on your hand, they look like an opalescent cloud. If they're periodic, they couple into light, and so you can see these really pretty colors. But it looks like a piece of aerogel or something like that that won't crumple in your hand. What you can see is that we're not limited to periodicity. We can write, these are all real SEM images. So nothing here is computer generated. So if you can see the scale bar here, this is about 5 microns. So the unit cells on the periodic ones here are maybe anywhere between 3 microns and maybe 15 microns or so. So your eye can't resolve any structural detail here. So that's why it looks just like a homogeneous material. So in a regular monolithic material, when you zoom in, the first level of organization you see is already at the atomic level. It can be the grains, it can be the atoms, it can be something, but it's already at the atomic level. What we do with these materials is that as you zoom in, you first see this kind of level organization before you start seeing the atomic properties. And because of that, they exhibit very unique properties, as you'll see later in the talk. You can see we're not limited to periodicity. So some of these, for example, some of these periodic ones are isotropic, some are anisotropic. What you can see, those of you who like Doctor Who, this is a nano-TARDIS. So I believe its dimensions are about 1,000th of your hair diameter, depending on your hair thickness. So one feature that you see right away is that these are all cellular solids. So they're very open structures. And of course, it's intuitive that they would be very open. So, but 99.9% air is a lot. And so this less obvious level of porosity comes from the fact that the tubes that comprise these nanolattices are all hollow. So here's a zoomed in image. And what you see is that each tube is hollow and the wall thickness can be on the order of 10 nanometers. Okay, so we're looking at a material that has every single length scale from 10 nanometers to maybe hundreds of nanometers to some microns to tens of microns and hundreds of microns, millimeters, and eventually centimeters. And so you can imagine that at every length scale, there are going to be unique properties that emerge. And so because of that, we feel it's appropriate to call these materials metamaterials because their overall properties can no longer be described purely from the structural perspective or purely from the material perspective. They play together to define a new set of properties in these new nano-architected metamaterials. Now, I told you that these were all very lightweight. Hopefully at this point I've convinced you of that. So the largest dimension of any solid here is just the wall thickness, right? So this is what I still have to convince you of, is that they're very strong, or they can be made much stronger than their monolithic counterparts. And for that, the reason why this is the case is because at the nanoscale, almost all rigid materials exhibit the so-called size effects. For example, if you look at some common metals like gold and nickel and silver and copper, and you look at a single crystal, so just one grain, they exhibit this ubiquitous smaller, stronger size effect. So yet again, this is a log-log plot. This is strength as a function of size. So when you reduce the dimensions of a single crystalline metal down to the nanoscale level, or at least micron and submicron level, they exhibit this smaller, stronger size effect in a power law fashion. This is a very strong size effect. Okay? Now, if you were to deposit these very same metals, gold and nickel and platinum, in a slightly different way, such that the nanostructure that you get, such that the microstructure that you get is nanocrystalline, so you have these very small grains, all of a sudden this effect is reversed. So it's exactly the same material that has a different atomic level microstructure, and now all of a sudden smaller is weaker. It's a more modest effect. It's not on the log-log plot, but it's still real. It's a pronounced size effect. So what you're learning from this is that, wait a minute, if I know both the nanometer size dimensions and the atomic level microstructure, I can use strength becomes a tuning knob, or both of those are tuning knobs for strength, so I can really control and tune my strength. But what's even more powerful is that the size effects don't manifest themselves only in strength. In fact, materials that are intrinsically brittle, like glasses, and I'm choosing metallic glass as an example here. So imagine a glass rod and try to pull on it. So that's what I'm going to show you. This is I believe, 100 nanometer diameter glass nanorod that we're going to pull on it. So my student Rachel is going to do this, and she's pulling on it. And so we all know what happens to a glass rod when you pull on it, right? It's going to snap. It's going to break. So this is a stress-strain type of data. So this is strain, and right here is 100%. So you can see that this particular glass fiber was able to deform by 100% before failing. So this would never be possible at the macro scale. If you look at a glass fiber, this would never happen. So materials that are intrinsically brittle can be made ductile by the virtue of the size reduction. Here's another example of a ceramic. So we know ceramics to be relatively tough materials. We also know that if you take a piece of chalk and you try to bend it, it'll snap, right? So let's look at the deformation of a ceramic unit cell in one of these nanolattices. We're compressing it, and you can see what's happening to these beam members here. They're bending. Ceramics are not supposed to do that. So this tensile stress component here exceeds 2 GPa. So at this point, most ceramics would absolutely fail, brittly fail. And you can see that in these nanotrusses, whose dimensions are 75 nanometers, are able to deform over multiple cycles without any kind of failure. So the takeaway message here is this. Sometimes materials get stronger. Sometimes materials get weaker, and sometimes we can stop them from breaking. These are all very unusual upside-down time properties. But all of these properties emerge only at the nanoscale. So how do we capture? So the big question was, how do we capture? Is it even possible to capture all of these properties that are offered only by the nanoscale and then proliferate them onto much larger scales? So this is where these three-dimensional architectures come into play. So imagine a two-dimensional nanoribbon, which exhibits all the useful and advantageous size effects, and now wrapping it around a three-dimensional architecture. So that's exactly what we wanted to see and to do. So just a few words on how we make them, if any of you would like to know. So we use a process called two-photon lithography to generate the original scaffold. So the way it works is that it's a laser, and there's a photosensitive polymer, and when the laser interacts with the polymer, it forms a voxel. It's an interaction volume in 3 dimensions, and within that volume, with each single laser pulse, it releases exactly 2 photons. And the 2 photons, first of all, allow you to get the resolution down to these nanometer type levels. And also they provide a sufficient amount of power to cross-link the polymer just within that voxel. And now that voxel is being rastered in 3 dimensions in space so that you can write just about any structure that you want. So in our world, complexity comes for free. Of course, it's a very time-consuming process because you're rastering a single point all through space, it's equally time-consuming to write a simple structure as it is to write a complicated structure, and I'll show you some of the more complex architectures that we've worked with. Now, for many of our projects, polymers are not something that we're interested in, so after we've created this polymer scaffold, and again, I chose to show you something periodic here, but it doesn't have to be. After that, we use the deposition technique that's most amenable to the material class that we are in fact interested in. For example, if you're interested in a semiconductor, you may use chemical vapor deposition or CVD. Or if you're interested in a metal, you can use sputtering or electroplating. If you're interested in gallium nitride or some kind of a light solid state lighting device, your best bet is to go to MBE or MOCVD or something like that. And after that, we coat the entire structure with this material of interest, only with a very thin layer of it, maybe up to 100 nanometers, no more than that. And what we do after that, usually our samples are made in these cube type configurations, maybe 100 by 100 by 100 microns. And out of the 6 faces of the cube, we expose 2 of them, And when we expose them, what we're able to do is etch away the entire polymer scaffold. So this entire scaffold that was so painstakingly written is completely gone. And this is what shows you why we end up with something that's hollow, that's comprised of an interwoven network of hollow tubes that's made out entirely of the material that you deposited, and the largest dimension of the solid here is whatever the wall thickness is, so it's less than 100 nanometers. So we're fully in the regime where you were expecting to see size effects. Now, I told you that all of our nanolattices, your eye can't resolve any of the structural detail. So to do all of our experiments so that we know what's going on and have a complete set of information, we have to perform them all in the various in situ nanomechanical instruments where we can not only apply the deformation but also observe it. So these are the so-called different inquisition devices. So these are all the sorts of torture devices that we apply to our materials. And here's an example. So my former student, Lauren, did this particular experiment. So this is a hollow gold nanolattice, and she's going to compress it. And now, so what we have is both the data in the accompanying video, and what you can start to notice right away, for example, is that the material starts deforming only at the interface with the substrate. And this part of the material doesn't even know that it's being compressed. So wouldn't you like to have this kind of material in your helmet or in any kind of packaging or in anything that you're trying to protect, where instead of transmitting the shock onto whatever is adjacent to it, it would take the deformation all upon itself. And what we can do is now correlate all the undulations in the stress strain data with the individual layer collapse. So this kind of a technique offers us a much more complete set of information than what you would be able to get without seeing what you're doing. Now, probably one of the main powers of this particular technique comes from our ability to do tension testing. So compression you can do blindly like this, but for tension you have to be able to grip one of your materials. And so this is one of those samples, one of these nanolattice type samples, which has a pre-fabricated notch in it. We wanted to understand its sensitivity to flaws. And so yet again, the same person, Lauren, is doing this experiment. So she's pulling on it, and you can see the crack that's opening up here, and you can see the loading curve. And at the same time, eventually you see the failure that occurs along this crack. And you would never know where the failure occurred or how it occurred without the ability to see it. Not to mention you'd never be able to grip it. And what's nice is that after we fabricate these, we can also model them very precisely with exactly the same geometry and try to use perhaps continuum models or any kinds of other kinds of models to understand their deformation and failure behavior. So now that I told you a little bit about how we make them and how we conduct our experiments, the big question still remains: can we observe the nanometer size effects in something that's much larger than a single nanostructure? So what this is, it's an octet hollow alumina nanolattice, and the wall thickness here is about 15 nanometers. Okay? So what we're going to do, what my student Lucas is going to do now, is he's going to compress it. So imagine a very porous coffee mug, something that has a lot of pores in it and very, very thin walls, right? So if you step on something like this, it'll shatter. It'll absolutely shatter. So let's see what happens. So Lucas is compressing it, and the whole thing shatters. We have a little nanosymmetry in our instrument, and this thing is dead. It's not good for anything. So what we see is that, of course, it crushes and dies, right? Now what we're going to do is we're going to repeat exactly the same experiment, and we're going to reduce the wall thickness by a factor of 5. So instead of 15 nanometer walls, we're now going to make 10 nanometer walls. Exactly the same material, exactly the same microstructure, exactly the same everything, but the wall thickness is different. So let's see what happens. So it should crumple even more. It should absolutely die, right? Because the walls just got thinner. So he's compressing it and compressing it a lot, and we're really expecting it to snap at any moment now. And it really doesn't. And not only does it not snap, but it recovers. So my student Lucas just made a ceramic. That's 99.9% error. That's relatively strong. That's completely damage tolerant. You can push on it there until you're blue in the face and it'll always recover. Ceramics are not supposed to do that. So if that doesn't teach you that the size effect is real, then this whole point of my talking here is completely lost. So the only difference between these two is the wall thickness. And so what you can see is that you can elicit entirely diametrically opposite behavior out of these. So now the reason why this happens, it turns out, is because of this critical ratio between the wall thickness and the radius of the tube. And so when you look at something that's only 10 nanometers thick, it fully recovers even after you've compressed it by more than 50%, by more than its height. It fully recovers. This image is of a post-deformed nanolattice, and you wouldn't even be able to tell the difference. It looks exactly the same. You can see this is true for all different sorts of unit cells every time it recovers. Now let's see what happens as you increase the wall thickness And you can see as you deviate farther and farther from this critical ratio of the wall thickness to the radius, your deformation becomes a lot more jerky, much more stochastic, up to the point where there's no even attempt at recovery. So this is what's important. It's important that we really understand these materials both from the material and from the structural perspective. Now, what we also are discovering now is that we don't just make nanolattices, the ones that I showed you, just as is. We also can make them be hierarchical. And the reason for that is bio-inspiration. You can have bio-inspired materials such that each one of these tubes is now comprised of self-similar unit cells, where you can see that they're also, so it's a nanolattice made out of nanolattices made out of nanolattices. And with that, we can really start to understand the behavior of real biological systems, for example. And it really improves the scaling. The video I wanted to show you it's one of these hierarchical nanolattices, and we're going to compress it. And so here's the pointy top. We collapse the pointy top first, and then we start kinking these. Yet again, this is a brittle ceramic, which we're expecting to break at any point now. You can see the kinking, very pronounced kinking right here in this beam. And as it's kinking, this is exactly where it's going to snap, probably here and here, right? This is a ceramic. And what you see is that it fully recovers. So by introducing these different levels of hierarchy, we can really study their behavior in much more complicated geometries. So with just the 1 minute left, I just want to spend a couple of words on some of the relevant technological applications for these, because maybe at this point you're thinking, okay, these are all pretty pictures, but what good are they? So the first talk that I gave at this conference was all on energy storage. So you can start thinking of electrodes. You can start thinking of anodes and cathode type materials in these made from these nano-architected materials. So this is an anode, a silicon anode made for a lithium-ion battery. The entire thing, instead of being hollow, is now made out entirely of copper with a silicon nanoribbon wrapped around it. So the copper is your electron conductor, and then the silicon, of course, is your ionic transport material. And what you can see is that this is my student Xiaosheng is lithiating it, so you can see the lithium ions going in and then the lithium ions going out. And we all know that the volumetric expansion is very pronounced in these, up to about 300%, and you can see there's no fracture, there's no breaking. So I'm not necessarily advocating that we start making batteries out of these, but what I am advocating is that in these types of geometries, you have full control over surface area, full control over mechanical properties, and full control of the materials that you're making. So you can make very effective test beds, or perhaps battery electrodes or something, or capacitors or some kind of devices that require these kinds of combinations of active layers. And just to prove to you that this is a true battery, here's some electrochemical data that was taken concurrently with this in situ lithiation video. Now, what we're also interested in is actually quite a few very diverse biomedical applications, starting from these types of nanolattices serving as effective three-dimensional cellular scaffolds. These are real fibroblasts, so these are effectively your bone cells that are proliferating on top of this scaffold. So we can either start writing bone, or we can try to understand how does the bone mineralize, how does the process of biomineralization occur, and also various implantable devices, very small implantable batteries, etc. So these are collaborations with UC San Francisco and with the City of Hope. We have a project on photonics. So it turns out that by the virtue of their geometry, these nanolattices can serve as three-dimensional photonic crystals because they're so periodic in 3 dimensions. And so what my student Vicky discovered is that not only are they photonic crystals, but they're very sensitive to strain. And so effectively they change color if you push on them. So if you subject even to relatively small deformations, or rather small strains, which correspond to a large deformation, it changes color. This is still all in the infrared range, but eventually we're going to get to the visible, so it'll change color if you push on it. Now, this is probably one of the most intriguing problems, and this is the last one, and that is biomimicking. So if you think about the real hard biological materials, this is a diatom. Turns out that I just learned after my previous talk that diatoms are like grass to all sorts of sea creatures. So a lot of creatures with sharp teeth eat these diatoms. So these diatoms are exceptionally strong. We found them, in fact, to have the highest specific strength of all the materials that have been reported to date. So these are made out entirely of silica, so effectively sand. And look at how neatly organized they are. They have these hierarchical hexagonal constructs with little holes and walls and who knows what else in there. And when you try to decipher it, it's very, very complicated. And then if you look at the butterfly wing, for example, and you zoom into it, you see these kagome lattices, which are some of the materials, some of the architectures we've been working with. And of course, we know that for a butterfly to lose a wing or to tear a wing would imply death. So it's very important to have a nanolattice that's particularly robust to fracture, like a kagome lattice. So nature has had millions of years of evolution to perfect all these designs, to get exactly the functionality that they want. But we can't solve this inverse problem. We can't look at the structure and say, oh, well, the reason why the hexagonal patterns were formed was, to get the fracture toughness, and then these other things were formed for this. We can't decouple and isolate a single parameter because we don't know what's caused by the biological functionality, what's caused for the structural robustness, and what specific role each one of these serves. But what we can do now is we can start solving the forward problem. We can make the architectures and the lattices out of exactly the same materials as the biological ones, with exactly the same dimensions and with the same architectures, and specifically isolate a single parameter to try to understand what is its role in the overall mechanical performance. And what I'm showing you here are these three images. And some of them are possibly biological, and some of them were possibly made in our group, or maybe all three of them are biological, or maybe all three of them were made in our group. And I invite you to guess which ones or which one might be which. You don't have to give me the answer. I don't want to put anyone on the spot here. But what I am hoping is that you're thinking about it, is that you're not quite sure, right? It could be one or the other. And that's the whole point. You're thinking about it. So it's hard to tell. It's hard to tell which ones are real and which ones are not. So I'll leave you with that and summarize here. So if you walk out of here saying, oh my God, I just heard a lot of stuff, here's the key message here. There's three. If you're clever about using three different things, the architecture that you're using, the nano size effect in the material, and the atomic level microstructure, you can start creating entirely new classes of materials whose properties are completely decoupled from one another. And the reason why you want to do this is so that all of these cute little children, some of which happen to be mine, will live in the world where you don't need the hearing aids, because we'll just be able to write the cochlea bone and implant it directly into your ear, so that your iPhone 83 will hold charge for a year without needing to be recharged, so that balloons no longer will have to be filled up with helium, because helium is a precious resource. We'll just be able to evacuate everything, because vacuum is lighter than air, and our materials are strong and stiff enough to hold it, where the Christmas ornaments, of course very relevant now, will never break, and where chocolate is going to be made into chocolate nanotrusses, which are 100% taste, 99.9% air, and 0.01% calories. Thank you.
We will now start the panel discussion, and I'm going to ask the panelists, but first I'm going to introduce them. The first panelist is Y.T. Cheng from the University of Kentucky, and he is a professor of material science at the University of Kentucky. He has a BSc in physics and mathematics, and his role here is he's the guest editor of this issue, and his research areas are biomedical devices and sustainable manufacturing. So please come up on stage. The next panelist is Monika Backhaus, recruit from Corning. Monika is a senior scientist at Corning Incorporated in Corning, New York, so she will represent the industry here. She was trained as a chemist and earned her PhD degree in physical chemistry at the University of Hanover in Germany. She joined Corning after 18 years of academic research experience, because before she was a research director at the CNRS in Paris and adjunct professor at Cornell University and a scientist at the Max Planck Institute. She holds 25 patent applications and is credited with 130 publications. One of the examples she is giving is the development of porous ceramics for diesel particulate filter applications and electrochemical NOx sensors and thermoelectrics. Please, Monika, come up stage. The next panelist is Greg Galvin. He's also an author in this issue, and he is chairman and CEO of a company, of actually 2 companies, and he's an inventor named in 58 patents, and he was named the Entrepreneur of the Year by Cornell University in 2014. He launched his first company in 1993 already, and now he is still CEO, and I would like to ask Greg Galvin to come on stage. Thank you. The next panelist is Judd Reddy. He's from Georgia Tech, and he's also one of the MIS Bulletin Volume organizers. He is the Deputy Director for Innovation Initiatives at Georgia Tech Institute for Materials. He has been adjunct professor in the School of Material Science and Engineering at Georgia Tech, and now he is has a lot of prizes also. I will not read them all, and as I said, he is the volume organizer for the MIS Bulletin. So please come up stage. And then the next panelist is Suresh Babu. He's from the Oak Ridge National Laboratory and the University of Tennessee. He is also an author in this issue. He obtained his PhD degree in material science and metallurgy from the University of Cambridge as well. And his work has been on both basic and applied research. One of the topics is 3D printing. He is using computational material science and computational and multi-scale characterization tools. He is a fellow of the American Welding Society and has also a lot of awards. And please come up stage, Suresh. So, and then, of course, I would like to ask the speakers to be members of the panel. So, Colin, would you please come up again? Julia had to leave, and Teresa also, I presented her already, so she should also be among the panelists. Okay, so we heard all your talks and opinions. You come from different worlds, from academic world and industry, and some of you have both experience. And now is the question to you, what is the most important part, or what comes first, material or application? And we can do it in the following way. You can ask questions, and if necessary, I will repeat them and address it to one of the panelists. So please, do you have questions to the panel? So if not, then maybe I'm asking you first, Monica. So you are coming from industry, and so what is your opinion? How much basic research do we need on materials, or is it better to find a patch for your problems?
So typically it's a pretty tight connection between both development of the materials and the technical application. So, and it's something which goes hand in hand over a long time, because typically the first pitch of a material is unfortunately not the best one. So basically there's a first material, there's a development of a first technology, the first process as well, and then basically step by step, loop by loop, it goes on. And I think this works probably best together with those inventors of the material, which means in many cases universities and research institutions, and basically someone who will really do the mass production of the material afterwards. If there's a startup company in between, it should be always something, basically collaboration all across the different levels, from the fundamental research up to basically engineering and production. That would, for me, be the most efficient way.
So as a basic researcher, this is of course very tricky to do so, because we always want to work on a breakthrough. Maybe you have an answer to this idea of Monica. Do you have a remark?
So the question is whether you want to focus on basic research or engineering. Is that the question?
Yeah.
So I think I would kind of twist the question as I would say the interface between the fundamental and the engineering is the most important. So in the way you can translate the basic to apply it quickly. So we used to do that quite often very well. And then as the things progress, so its departure quite a lot happens. So a lot of people in the interface area between the applied and the basic is reduced. So we need more of those people so that they can translate back and forth. So as explained by Colin.
So this interface person would be the CEO who's working for free, or what is this interface?
I would say actually Colin actually acted as an interface here. So if you remember his talk, clearly that he could negotiate the deals and everything. Still, you won't call it CEO, but I really enjoyed the talk. So.
Okay. Yeah, but you said that you were not a good choice as CEO.
No, I think I just didn't have the experience of running companies. So, if I've run a few more companies and I might, get involved with a few more, I might be, that's right. But I think for a CEO, you do need someone who has developed a successful company, got a track record, and then bring that person on board.
I see a lot of students in the audience, and I think it's very important for them to take at least one business class while they're taking their scientific and engineering classes, because if you when you get out, you may go to industry or you may go to academia. If you go to academia, you're essentially running your own business, writing proposals and developing a product, which may be a proposal or some peer-reviewed paper, or the students, yes, as well. But having the ability to speak both the scientific language and the business language and serve as an effective translator between those two worlds can really help your career, I think.
So do you agree with this statement? Do you really want to do both, being a good scientist and also understanding something about money and business plans and so on? Do you think it's a good idea to have both? Yeah, please.
I think that's a really good idea, because in the end you're trying to contribute to society and you're doing research on a small scale in the lab, and if you do not know how to put this out there in industry for a large scale application, if you don't know how to, how should I say, move towards a patent, move towards these production processes which make your small product into a large product, then yeah, I think indeed it is necessary to also know the more economic and more the business aspect of science, actually. So I do agree with that. So in my university, we're basically obliged to take a course like this because they do value and appreciate that aspect very much. So I do agree with that, yes.
So I have a different question. So
yes, okay, sorry.
Many researchers from academia see applied research as a dirty word, and so you have a lot of really smart people that are discovering a lot of new things and have a lot of knowledge. They can contribute to some of the problems that industry has or industry would like to pursue. We used to do this better way back when. How do you see us doing that better in making a bridge between industry and some of the fundamental research that people are doing and not thinking about applications?
Yeah, Teresa, please.
So I think it's very important for industry to have close ties with, some set of universities so they can see what's going on, but more importantly, provide input on what the important problems are. I think even though many faculty are only interested in the basics, they still have a choice about which direction to look in. And so it's up to you to sort of say, look, there's something interesting over there. And that's the first thing. The second thing is, I think, at least in the US, companies have gotten used to all the basic research being taken care of by the government, and that's increasingly untrue. And it may be untrue for the topics that you care about. So there has to be sort of engagement and building of collaborations and not huge exchange of resources, but some. And I think that's how people get interested.
One of the key challenges I see on a daily basis is most academic folks, if they want a research grant or a research contract, they want that to last 3 years or so that you can get your student well enough along that they'll graduate. 3 years is forever on an industry time frame. They want more like 6-month or 18-month type contracts and research efforts, and that's really scary for me to bring in a graduate student and put them on this effort that I know is going to last a year, maybe tops. What happens at the end of the year if I'm no good at my job and I don't have follow-on funding? I don't want to turn, I can't fire my student, or I guess I could, but I'm not going to. And so it just learning how to have, I guess, a diversity of staff. So postdocs can really work very well on the 6 to 18-month time frame, and team with the graduate students as well as the undergraduates to get the different efforts forward.
Yeah, it's a very good idea to work in a team so not everyone has to do everything. So please, you have another question.
Yeah, I recently moved from a national lab to industry. So what I see is a conflict between the metrics in which academic or national lab research is weighted, that is papers and publications, whereas in most industry, it is by quarterly profits or something, which are totally diametrically pulling the research apart. And I think there needs to be more bridge between those two in terms of some reasonable metrics which would bridge this gulf.
Thank you. Steve had a question. Okay. So maybe first, okay. Gopal decides. He has a microphone.
I just wanted to respond to your point.
Okay.
In academia, it's actually not 3 years. It takes closer to 4.5 or 5 years to get a PhD out. But I'd argue that we do research at exactly the same pace as they do in industry. A graduate student has a very non-linear output. Nothing, 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 and then they do everything in the last 6 months, and they get just as much output in that time. And education includes preparing a student and preparing the human capital. So it is amazing that that's how it usually works, and I think it's important to say that. So.
May I add a few things to this discussion? I worked in industry for 20 years before I became a professor. To me, I don't see a clear boundary between basic and applied research. I think it's a continuum. In terms of how to improve education, my students are supported, co-supervised actually, with a co-advisory industry. And they work on problems that of immediate interest to industry. And then I think by doing that, one can cover both applied aspects of the project and also look into the fundamentals at the same time.
Okay, sorry. Next question, please.
Yeah, I think as a follow-up to some of the earlier comments, in basic research in the universities, very often you have absolutely no clue what your product will lead to. Absolutely none. And if we look at the development of some of the things we take for granted here, we find that in the days when they were studying it, they had absolutely no clue as to what will happen 20, 30 years from now. So even the 5-year time scale often is so small. I mean, if we look at all the technology, the cell phones and all those things, it took decades for the basic work to be done. And I think we have to recognize that as we think about applications and how to make sure that we don't lose that.
But I'd say also there's another distinction to be made. I agree with the concept that basic to applied is a continuum, but when we talk about basic research and commercial output, we're often referring to a fundamental discovery that then ultimately became a major commercial success in some fashion. And if you look historically at fundamental new discoveries, they tend to take about 30 years to mature into a real significant commercial reality. And 30 years is even worse than 5 years on the industrial timescale. And that's typically 3 venture funds' lives before anyone starts to make money on it. So that, you know, basic research where you're trying to better understand the actual mechanics of how this thing deforms is different than basic research of a fundamental new discovery that generates a whole new industry.
And I think that's something very important, because one of the key roles of the universities in material science, physics and chemistry is to create this fundamental knowledge and provide the maximum of learning of materials, new structures and designs, to have something like a big rubber boat around materials and new inventions, because it's basically this fundamental knowledge which helps afterwards to understand and build new materials. And that's one of the key roles of universities.
Thank you.
Yeah. I think in US you are at a good point where you really have a collaboration between basic scientists and people working in industry, but I think in other parts of the world this doesn't work yet so well. I think about Europe, at least where I have been doing my research experience up to now. They are encouraging us at the university to apply for funding together with the industry. But in my experience, the industries are kind of waiting to see that we at the university produce good results they can use and commercialize. I don't see really, I don't know if you have other experience, Anke, I don't see really a collaboration between the two. How can we improve this collaboration?
Okay, let me take a crack at it. So in US, in National Science Foundation, they have a program called Industry University Collaborative Research Center. It's called IUCRC. So this is what it really does, is a franchise to bring industry, academia, and government agents to have a communication. So more than the technology, so you need to have a credibility, you need to create a trust with them. So before, money comes as a membership from the industry to fund it. So in fact, the IUCRC, NSF puts a very little amount of money. The most of the funding comes from the industry. But that requires the faculty to talk to the industry and then understand their business need and then translate them to fundamental or applied science need. That way you can develop a credibility and trustworthy with them. So most of people who are here have done that in the past. So, but it is the one which I would always say that first thing is handshake and say, rather than professing about your expertise, you need to listen to what their problems are. So that is the first and foremost. I'll stop.
Thank you. Is this answering your question a bit? Is this missing?
You're European, please. Just to say that in the UK, there's some big companies like Rolls-Royce that have detailed collaborations with universities, and they set up what are called university technology centres, and some of the Rolls-Royce centres are in Europe and some are in America, I believe. And that really works very well. So the Rolls-Royce person and the university people, they discuss joint projects together, and they get something which is of mutual interest to both parties. But from both sides, it requires a lot of work. It's a lot of time. So it's much easier to be an academic that doesn't talk to industry than to be an academic that does talk to industry. And so that's the culture we really need to develop. And the same for industry. You know, industry needs to develop a culture of talking to the academics. Then both parties can benefit.
I would echo what Colin said. It's work. It's very hard work. But one thing that does unify industry and universities often is the advanced instrumentation that universities have, because companies, you know, not every company wants to own that instrumentation, and they don't want to employ the people to use it and maintain it. And so building on instrumentation is a good way of making that interaction or initiating that interaction.
So to capture industry partners, you have to show your expensive equipment, please, and competence.
Hello. So I'm a graduate student that will soon graduate, and I'm thinking forward of when I'd like to be an academic and start my own lab. And I've been really impressed with this coming down to you need to have that communication between the lab and industry. How do you go about starting one of those types of communication, or how do you start that communication?
Places like this.
Okay.
It's all about the networking. You may not realize it, but you started your networking several years ago by presenting your work at symposia and writing papers, and that's essentially your advertising, if you will. And you just slowly make friends, and those colleagues may be in academia. They may wander over to industry or back and forth to national labs or wherever. And just as your network builds and people learn your capabilities, you get friendly introductions. There's also, at least in Georgia Tech's case, we've got a very active alumni base that is, Georgia Tech turns out the most engineers of any U.S. institution, so we've got spies all over the place. And those spies identify problems throughout their industry, and they come back and they talk to their old professors, they talk to their old schoolmate chums and whatnot, and we listen. That's the most important thing, is to be a listener, but you need to be a quick listener, because again, it's the pace of industry. They really operate at my experience is that it operates at a much higher level than academic type folks, because they don't have spring break that gets in the way, and final exams and other things that kill off productivity for weeks at a time.
Yeah, I would absolutely echo two of those points. Although I'm representing industry here, I also have heavy engagement with Cornell, and accessing the alumni base is just incredibly valuable, and I would say one of the largely overlooked opportunities for making connections. And then the other would be kind of the inverse of your question. I was asked to serve on a panel of mostly life science postgraduates who wanted to not go into an academic career and had kind of been predestined towards that path all the way up to that point. And they asked the inverse of your question of, okay, how do I not become an academic? And the answer again was networking. And one of them who was there emailed me afterwards, and she's now working for my company.
Very good. Thank you.
So may I ask, add on to that, one of the things as a graduate student, you should experiment. Next time when you are on the flight, next door, ask a person, where is he working from? If he knows from industry, make a pitch about your research, how it relates to them. Believe it or not, I did once and then had a project with that.
Very good.
I completely agree about that. The socialization, we're coming up on the holiday season, so there'll be a lot of party opportunities typically to go to, and standing around mingling with folks. So what do you do? I'm a material scientist, and they just sort of look at me and, so how about those Braves? They're signing a good pitcher next year. So to be able to convey your science in a meaningful way that resonates with the common man or woman is very important. I was just up in Chapel Hill, where I'm from, having Thanksgiving with my mom, and she doesn't care one lick about my peer-reviewed papers, but she's very, very interested in the solar cell technology we've licensed. She always wants to know how that's coming along. She doesn't care that I'm drafting a terribly difficult paper to write.
Okay, we have another comment from the...
I have a new question to ask.
Okay.
You do know that the federal government has requested funding agencies to require PIs to make their data and their research open access to the public. And so as we struggle to do this with respect to data management plans or handling data, there's a great opportunity there for learning how to use that data in new ways to learn new things. But also there's the problem of sharing that data. How do those two conflicting ideas affect the relationship between academia and industry to move forward in a productive way?
Well, the federal actions that you're discussing typically apply to federally funded research as opposed to industry-funded research. So industry is very, very close to the vest with the IP and whatnot. That's been my personal experience.
Set the rules of engagement up front. so that there is no surprises as you're moving forward with the project. Okay, they are open to sharing some of the data as long as it's pre-competitive.
Pre-competitive, and you say process A, process B, as opposed to explicitly delineating out the secret sauce of an industrial application.
There was one other comment from you? No? Okay.
I would say that the open data issue is it's complicated because a lot of time nobody wants to host the data, right? So the journals, the publishers are all doing experiments, if you will, on data and how to share it and how to keep it. The MRS is worried about this. I think there's a data session maybe right now or yesterday at this time. So it's evolving quickly, I would say, and it's not clear where it will end up. But I'm pretty sure it'll be a better place eventually.
Thank you. More questions, remarks on this issue?
So I'm just curious, since we have these amazing people up there, about 15 years ago, maybe 20 years ago, we saw the total collapse and demise of the Industrial Research Laboratory. Bell Labs went away, IBM's all but gone, Xerox, Exxon are all gone, Westinghouse is gone, and yet here we are continuing to innovate and create new materials and new products. How have we gotten away from that? Do you think that that was an essential thing to have those industrial research labs? Or are we just in a gap where they did enough great work that we're still living off the fruits of what they did? Or do you think we're going to be in a crisis soon because we don't have such an endeavor? Because the governments, while they continue to fund, the total amount of funding, is still gone way down compared to what we used to have with those worldwide treasures, I would think. So how is it getting done? And how is it going to get done in the future with that gap? Is it going to happen at the entrepreneurial level? It's not happening in industry, right? They're not doing that kind of research that Bell Labs or IBM or Westinghouse used to do. So maybe that asks the question of how valuable is basic research. I've always contended it's wonderful as a training ground for human potential. But I still remember when I was a postdoc at Bell Labs, my boss telling me, there's wonderful problems out there that are all basic research. Why not work on something that might be useful? And we all did applied basic research, and that's what we did. So I'd like to know your thoughts on that.
Well, you probably, being from Bell Labs, read the book, The Idea Factory.
I won't read it because it's too depressing.
It does not end well. You're right. It's pretty exciting, good plot and character development, but at the end it's kind of rough. But I do recommend that you read it and have some tissues with you when you do. But it's very insightful because it describes exactly what you're saying. And I think the role of a lot of those have been taken over by academic institutions. For instance, Georgia Tech has what's known as GTRI, Georgia Tech Research Institute, which is the applied research arm. And I've got a joint appointment there. So it's like having a foot in academia as well as industry at the same time, and allows me to hop back and forth. Other places have Lincoln Labs and SRL and a variety of different quasi-academic labs that are grounded in the basic science, because that's fundamental to everything, but also have an eye on the application and the future. It's, as Teresa was mentioning earlier, that the federal government seems to have, everybody's ceded that the federal government will fund the basic research, and that is going away. So if we're not careful, we'll lose our seed corn and the whole crop.
But I'll take a little issue with some of your comments. I largely agree with it, but if you look at some of the companies you mentioned, IBM, Xerox, I mean, they still have multi-billion-dollar annual research budget. They're still doing a lot of research. It's not what it was 30 years ago. But also, if you look at most American corporations, they're nothing like they were 30 years ago. And I think the generic answer to your question is all activities have been distributed. And so the whole research enterprise is much more distributed across types of institutions and across geographies. I mean, the gallium nitride that was mentioned earlier, came out of an academic lab and is now growing into large new corporate activity. It didn't come from the guys who were making light bulbs before. It didn't come out of the corporate researchers who you would logically have thought might be doing that. And so I think we see research innovation occurring in lots and lots of different formats, and it's not in the four big corporate labs that it was 40 years ago.
Comment?
I mean, corporate labs are still there, right? I'm more familiar with the car industry. General Motors, Ford, they all have research labs in existence. Even at this MRS meeting, we have met several car companies making presentations on topics like lithium-ion batteries. So, in fact, the students, they're still hiring PhDs. One of my first PhDs now hired by the car companies.
So Steve, I think part of it is that the world has changed a lot, right? It used to be that the thing that was so special about Bell Labs was the way that people interacted in a very interdisciplinary way. And that just didn't happen at universities at that time, right? So universities have become much more interdisciplinary. And from the company end, it's much easier for them to interact with academics than it ever was. Just fire up the Skype and find out what's going on. So I think all the ways of communicating have changed enough that you don't need one giant research lab sitting physically somewhere.
You misinterpreted. I wasn't making a statement. I was asking a question. And I think the answer to the question is probably that we don't really need those big, former, huge basic research labs. I think, and I was just asking, how is it going to move on in the future? Because I think we've hit a whole new way of doing things. And I'm not sure we've recognized really where the strengths are coming from. And that's what I wanted to ask. What's going to happen in the future? That's what this is about. And the central research and development things are going down. They're still there, sure, but they're a fraction. But I'm not bemoaning their absence. I'd just like to know where we're going and how we're filling
I think you have one model for that in the life science world, where the large pharma companies, which once upon a time ran $40 billion central research operations, have all but abandoned it. And the model is entirely little startups, high risk, funded by the venture community, try the risky science. When it starts to look like there's promise there, they get bought by the big pharma who can put it into the distribution and commercialization path. And it's just completely altered the drug discovery model for that industry. Whether that happens in the physical sciences, I don't know, but that's one example.
And it seems like everything in society is going to the distributed model, and research is no different. I think that's a good thing. I think that there's plenty of good ideas scattered all across the globe that can be capitalized upon.
There is one resource which across the US you have a DOE national labs. They do work with industries too. So in fact they come and do a lot of CRADA with them. So indeed those are the resources which you can use them, and across the board we have a lot of them. So bringing universities, industries together, they could be the nexus of them.
Thank you. Other further questions, please.
So I recently became a postdoc, and I'm also president of a small company that we started based on some IP we developed in our research. And we're trying to find funding, and navigating the landscape is a little overwhelming. And we were pursuing some SBIR grants and some goalie funding potentially, and then we're also pursuing partnerships with companies that already do federal research, as well as some companies that just produce products, like we do aerospace materials, so Boeing and things like that. And so it's hard to identify where we want to focus our efforts. And I was just wondering if you had any advice, as someone getting started, what is sort of the best bang for your buck, if there is such an answer in that?
Are you geographically fortunate in that you're located near the Bay Area or Boston or other sorts of areas? Because there's definitely areas where venture capitalists and angels tend to roost a good bit more. Georgia is not really one of them, where I'm from. It's growing. We're getting more of that environment, but most of the investors in Georgia are more interested in real estate as opposed to carbon nanotubes. That, unfortunately, at least from my perspective, seems to be very, very important. Even though I'm in Atlanta and you can get to Atlanta Hartsfield from anywhere, it's only a few hours from the Bay Area. It's a giant chasm between there.
Yeah, that geography plays, unfortunately, a huge role there. Central New York is worse than Atlanta. We have managed to rank last every year in total venture funding in the country. But the answer is really, there is no one answer. It's all the things that you mentioned. It's back to our soon-to-graduate person's question. It's all about networking. I mean, we say that there's lots of money in Silicon Valley, lots of venture firms, and there are. But there's also all that much more competition for their money, their time. So I may have seen many startups leave Cornell and say, oh, I'm going to go out to the Bay Area and get funded, and they don't get funded. Because at the end of the day, funding tends to be all about who do you know and how can you establish credibility with the people who have the money. And that's all about networking and perseverance.
Before I came to Georgia Tech, after graduating, I worked in industry for big business and then worked at a small business doing SBIR. And that's really a great program. The phase ones are, and for those that don't know, it's SBIR, Small Business Innovative Research. It's a funding mechanism. And phase ones are challenging to do. That the money allocated for that effort is really usually not enough to actually do the effort. But it's good seed to get to the phase 2, which actually does tend to be enough. And then if you're even better than that, get into phase 3 and commercialization is the way to go. I'm a big fan of the SBIR program, and STTR is its evil twin cousin.
Yeah, I may add to this point that you may want to be a big fish in a small pond. Kentucky is probably one of the poorest states in the country, but we do have a one-to-one match to SBIR. If you won the SBIR, the state government will provide one-to-one match, both stage 1 and stage 2.
He speaks the truth because the small company I worked for up and left Atlanta for Kentucky.
Okay, since the state wars are on, you are welcome to come to Tennessee, please. And there are a lot of opportunities in the nexus of the UT, ORNL, Y12. There is a lot of focus on small business innovation. And a real tangible example is my grad student who worked with me started a company called Aditerra, so right next door to Oak Ridge National Lab.
So if I could just say one last thing, Jonathan, and he's fortunate to live in California. I think Colin said this, actually. It's sort of a matter of convincing people that you're almost there, right? Because it's so much easier for them to invest in software than in hardware and real materials. And so certainly in the Bay Area, it's a much more distributed model, right? When you start a company, you outsource everything. You don't do anything on your own. It's like you said, you have an office and there's nothing there. And so convincing them that you're almost there and you don't need many resources, whether or not that's true, seems to be part of the problem.
Yeah, again, the development timeline is exactly right. The materials is, you tend not to have that magical breakthrough that 6 to 12 months later, you've got this product that you can put a barcode on and start selling.
So one of the things which is often missing, I think it's good to have networking and have the right contacts, but it's very important as well to have basically in an early stage already a cost model, and in the cost model a variation of different parameters and inputs to basically see where are the key drivers for your product, where are the key obstacles. And sometimes you figure out maybe it wasn't really your invention, your material, but it's some kind of sidestep. And typically, you would know how to address that. But if you go now and sell your product somewhere, they would look at it and say, this does not work. It's too expensive at some point. So I think it's very important to do this kind of exercise around cost modeling very early, just to be able to address obstacles and basically have a nice proposal.
Yeah, definitely do your homework with the customer engagement. Whoever's going to ultimately buy your product, know what they're wanting for it. We're developing a medical technology, and as we started talking with nurses and other practitioners at hospitals, they identified a whole new area that our product could be used for training, that they spend a whole bunch of money training, that we had never, we were just going to prevent infections. But there's just an area that we didn't even know about till we started talking really in depth over beers, and you buy them dinner and stuff like that, and it's just called overhead.
Maybe I'll add to this point. I think this is a really important point, distinguishing academic research and industrial research. Rarely a material is used just because of one attribute. It's a multiple attribute in the material. Initial performance, durability, safety, and cost. And academic research often is only focusing on one fashionable data point that can get people into high-impact journals. Whereas industrial research, you have to simultaneously study a number of parameters, including cost.
Yeah, academics never focus on cost. I can vouch for that, for sure.
Thank you all very much.
Are there other comments, questions to the panel? So do we really find great ideas, great breakthroughs when we are thinking about costs? Is this really the conclusion?
No, you find the great breakthrough just, through our own curiosity and everything. It's coming up with clever ways to make that breakthrough viable in the real world.
Okay.
So the real entrepreneur, first of all, thinks about customer need. What is he trying to? So, for example, one of the example is what is a human need? What do you like to focus on? That may be pretty expensive when you start off. Probably, if you think about one iPhone you created, maybe $1 million. So, how it makes an impact, you have to focus on. The cost is not the first thing.
Thank you.
So I have really some sympathy for the energy sector, and I have worked in many different projects around energy. And there's, for example, a very large difference, since we come back to cost, in the energy sector in Europe and in the US. So in Europe, the government supports research, initial industry efforts to basically develop new materials, new systems, new designs, whatever it is, to create green energy. However, in the US, there is not such driver. It's just the market competition, right? And so many of those actions which could be taken have to be driven by laws. So once the laws are established, basically industry can come in and say, okay, we can work in these areas. But before, while we don't have actually a legislative decision to drive some new laws and regulations, it is almost not possible to do so. While in Europe, I think the governments really provide a lot of money to drive it in that direction. And I think this is an area, the energy sector, where work in Europe is much, much easier between research, universities, government labs and industry than it's in the US, for example.
Yep.
To my large regret.
Thank you. Okay. So there's a...
So one of the things about if you're in academia and you build up skills, you build this hammer and you look around for nails. And so it's straightforward maybe to get funding if you can make it seem like you found a nail. But that may not be true. So are there any funding mechanisms if you found a real nail but you don't know what the hammer is yet?
Okay, let me start off with when I finished my PhD, I was very happy I came out, and Professor Badisha said that, Suresh, you just got a driver's license. So that means what you learned in the PhD is how to analyze the problem and how to go about solving the problem. It is not one hammer you have. You have an ability to multiple hammers or multiple tools to go and solve an engineering problem. So that is the most underlying principle what we have to learn from the first point on it. So then comes listening. One of the things is about understanding each other's problem and being sympathetic to what their problem is. And then coming up with, sometimes you may not have a solution, but your colleague next door will have a solution. Go drag him out for a beer or something, and then figure out how to fix the problem. So that is the best way to go about it. So that's my suggestion.
The multidisciplinary aspect that you just mentioned is crucial. I think all the solutions that require just one little skill set are solved at this point, perhaps, and that all the, at least in my opinion, all the future very difficult problems really require a material scientist, an electrical engineer, a mechanical engineer, a computer scientist to work collaboratively as a team to solve that. And I've certainly never in my experience had an easy time with funding. I think the average tends to be about 10% hit rate for most people's proposals and whatnot.
Okay, thank you.
Thank you. Okay. So if there are no more questions from the audience, is there something you want to say and you didn't say now?
There is one area which not been discussed. Is there is a new generation of students and everybody. They are actually, it's called maker community. They are not waiting for us. So they are going and innovating. They are thinking about it, totally different ways of going about it. So sometimes if we can get their enthusiasm instilled on us, wow, that would be the future. So think about it whenever you have it. So there are so much of tools you have it readily available. I wish I can go back and do my PhD right now. So that the information is right there. Only thing you need to know is how to ask the right question.
Yeah, the concept of makerspaces is a great invention. And if you don't have it at your academic institution, you need to start banging on department chairs' doors and those sorts of things. And make sure that, she's got one, so it's no trouble. But to make sure that those assets are available to you to allow your creativity to explode onto the marketplace or into the journals, wherever it may go.
Okay.
Oh, I just want to use the opportunity as one of the volume organizers of the special volume to thank the other volume organizers, editors who are not here, Dr. Arun from India, Banerjee from India, and Professor Jim Williams. And also Gopal, MR staff, Cambridge University Press. Of course, the authors and the reviewers, if you are in the audience, if you're not in, thank you all for contributing to this volume.
Okay. So Paul will give the last words, but I would like, before he's coming up and summarizing, I would like to thank you all for your time, this nice discussion, and good questions from the audience. And hopefully we will have big breakthroughs soon with this collaboration.
Thanks, Anka. Yeah, so just a few closing remarks. I mean, I was really struck. No one really asked to challenge the basic premise of the issue, that is the interplay between materials and engineering. And maybe it's a little self-serving, because if you're coming to this conference, you probably fundamentally believe that materials have something to do with improving life and pushing on engineering. But you know, I think that is a fundamental truth. There's plenty of history that shows that materials and engineering have played together. I know in the industry that I'm in, electronics right now, because of the growth of information technology, getting copycat technology for products that you make is happening faster and faster. So there's a huge pressure to keep differentiating your products so you can charge a little bit higher prices, get higher profit margins. So industry really, really does need new technology. New materials does enable a lot of that. I was struck by Teresa's comment about materials equal risk, for sure. I think having worked in both startups and big companies, one kind of rule of thought is that every time you scale the volume by a factor of 10, you discover some fundamental flaw that's really going to kill the product, and you have to overcome that multiple times.
in those cases, having the fundamental knowledge of how the system works, how to tweak things to overcome that, or just persevering and pushing it through is really necessary. So I think an ecosystem of basic kind of sort of translational and applied research is really necessary for this, for this balance between materials and engineering to continue. So anyway, good discussion. Thanks to the panelists. Thanks to the MRS for sponsoring this special issue, and thank you all for coming. Yep.